Hello my friends, let's have a look at the Trigonometry AA HL revision session. I have prepared 50 questions, uniquely determined for triangles and equations and functions. And let's see what benefit we can learn from this revision session. So I did not create all those repeating questions. They are all pretty much independent. So make sure if you struggle with one type of question, you jump into the textbook and try to find something similar and see yourself if you can apply the skills that we have learned accordingly in this class. Okay? So without further ado, let's get started. So many contents, the triangle, circular measure, equations and functions and induction, all that jazz is so beautiful. So let's get right on to the business. So now I'm gonna have a look at the the triangle. Okay, so for triangle questions, what you need to always remember is that you need to look at the classification of the triangle. You know, if it's a SSS or SAS or ASA or SSA. Right? So all those classification can give you different types of questions that we have to deal with. In this problem, we are looking at SSS, that will be cosine rule, isn't it? So that's great. So from that cosine rule, the question, even though it does not tell you that it's about the cosine rule, I know I'm going to use cosine rule. So that's great. So it says what? Explain why the side that must be the longest side of the triangle. Oh well, you can then try the inequality. For example, if I try the first inequality, let's say, suppose it wasn't. Suppose it was smaller than the other one. For example, imagine n squared plus n plus 1 is less than or equal to 2n plus 1. Let's suppose. I don't know. Right? So if I did, then 1 cancels out, n cancels out. So the only thing that's left over here is that n squared is less than n, right? Because I subtract by n of the 2n. And then if n is strictly bigger than 1, that's a condition. So it says then what? N is less than or equal to 1 if I divide it by n, which is a contradiction to my given statement. So, you can prove this way that this is going to be actually the largest. So no problem. Easy peasy, lemon squeezy. And let's have a look at the show that the largest angle theta of the triangle is 120 degrees. Okay, so for triangle or trigonometry, if you can visualize the problem, try. Okay, so if I have A, B, C, and suppose that A was the largest side, largest angle, in the triangle, the largest side will be given opposite to the largest angle. So that is a great. So I got the angle A here. Okay, so that's great. So I am claiming that the opposites to that angle must be, what is it? N squared plus n plus 1. We know that is true. Okay. Now, as I've told you before, this is a SSS, isn't it? Okay, so because it's SSS, I'm going to do, what is it? The cosine rule here, my friends. So I'm going to go with cosine A, right? And then, I can use the cosine rule here, right? So if I quickly use the cosine rule here, what am I going to get? It's going to be, 2n plus 1 squared plus n squared minus 1 squared minus n squared plus n plus 1 over twice of 2n plus 1 times n squared minus 1. Oh my God, quite a bit of algebra, isn't it? And I strongly encourage you to do it. Okay, sometimes you need to get your hands dirty, and it's inevitable, my friend. So if you do the classification, it gets to be a negative half. So you see that the angle will be an angle from 0 to 180 because we're dealing with, what is it, my friend, triangle. So it needs to be between 0 and 180. That will make the cosine to be negative half, right? So now it only goes by on the first and second quadrant on the xy plane. Then for cosine to be negative, it must be in the second quadrant, and special angle that makes cosine to be 60. Cosine to be half is 60. So I'm going to do the reference angle. So 60 going up, so it should be, A should be, what is it, 120 degrees. So that's how you can find it, my friend. Okay, so make sure, yes, we need to get our hands dirty, so it's inevitable. So I kind of skipped this process here because I didn't want to bother expanding, but you should expand. All right. So one thing that I would probably give you a clue here is that this is simple expansion because it's a binomial, but this is a trinomial. And if I quickly remind you again from the algebra, a plus b plus c squared, if it's a trinomial expansion with the power 2, it becomes a squared plus b squared plus c squared plus twice of AB, BC, and CA is how you solve it. Okay, that's great. Okay, let's move on to the next problem. Here it says what? ABC of the right angle triangle, okay, bisect by the segment BD. Okay, so that BD bisects the angle, which is represented as an X. That's great. Okay, find the exact length of BD. I want to find the exact length of BD. All right, so that's great. So, but here's the thing, you know, from now on, when you do the revision on the trigonometry, what I really want to remind you here is that you understand what steps we have to take. And then here, you know, what steps should I take? I got the right angle triangle, all right? And then I got a sense that I must use the SOHCAHTOA, right? Because it's a right angle. You know, it's a right angle, my friend. It's a, you know, SOHCAHTOA. That's one thing. And number two, come on, man, it's got the bisected here. So I'm sure this is going to be something with the double angle. I'm sure it is. Okay, I'm sure it is. So let's try to remind ourselves with those things and then see if we can apply them correctly, okay? Let's get to it. So, sure, you know what? My job is to find the exact length of BD, so I'm going to call it maybe Y. I'm going to call it Y there, all right? Why not? And then, what else should I do? Given in the diagram, find the exact length, explain the simplest form. All right, sure. So, you know what? Let me call this as C, because it's opposite to the angle C. And then, let's try to see if you can find any value. So, hold on a sec. Let me see. If it's a right angle bisected by the segment BD, the length of AB are given in the diagram. Hold on a sec. Length is supposed to be given, but it's not given here, sorry. AB and BC must be given. AB is given, and BC is given. You know what? Let's call it A. So let's suppose that it was given as A and C. No problem. Suppose it was known. A and C are known. Y is unknown. Okay. So that's the only thing that we have to assume. So that's great. So A and C are given. Okay, so that's great. So then, yes, now the problem is done, right? Because for the Y and C to associate with the SOHCAHTOA of the right angle triangle, I'm going to go with who? Very good. I'm going to go with the cosine. So let's go. So cosine X is going to be, what is it? Voila, C over Y, right? The ka adjacent over the hypotenuse. No problem. And the cosine 2X is going to be who? Oh la la, C over A, right? So that's great. So then I can use the double angle, right? The cosine double angle that involves just in terms of cosine, so that I can substitute this. It's going to be 2 cosine squared X minus 1. That is great. So then I'm going to plug it in. If I plug it in, it becomes, what is it? 2 times. If you square that, you get the C squared over Y squared minus 1, right? So that's great. Then you're done, because if I put it into the common denominator here, my friend, what do I get? I would not put it into the common denominator, but let's call that as so this is a C over A. Okay, then let's try to rearrange. So what I'm going to do is rearrange that to the other side. So I got the 2C squared over Y squared is equal to C plus A over A. And voila, that is good. So then the Y squared is going to be, what is it? 2AC squared over C plus A is what I've got, right? So then if you want to get the Y, then I would take a square root of it, then you're good to go. Okay, so make sure when you see a problem like this, before jumping into it, make sure you read the question carefully and see what skills you can apply. For me, it was obvious, not obvious, it was natural for me to start thinking deductively that I'm dealing with the right angle triangle. Maybe it's a big deal for me to work with the SOHCAHTOA. And then number 2, it's a bisected. So that means double angle must be in hand. Okay, so that's great. So that's the problem for that one. Let's move into the next problem here. So now I got another very nice quadrilateral here. So right angle here, the x were given. And the BEA, it's not on scale, my friend. It's not on scale, but it says it's 90 degree, okay? Ha ha ha. All right, and then what were we given? CD was 1 unit, okay. And then DE was 3. Now we want to find what? Cosine DEA. So if I highlight the angle for you, so now you're looking for who? Cosine DEA, which is the same as cosine 90 degree plus 2x is what you're looking for. Okay, that's great. But here's the thing, you know, it must urge you to see the 90 either in sine, cosine, tangent, because it's something to do with the complementary angle. And now I see the complementary angle, I know inevitably that I will convert into something of a sine. So there's no doubt about that. But you need to determine whether it's going to be positive or negative. Well, the thing is, if you rotate around, I went 90 and added by 2x, I send it to the second quadrant where the cosine would have become negative. So I know the negative sign must be in the front of a sine. So that's something with the complementary angle. This is not reference angle. This is a complementary angle with the 90 degree here. So actually the simpler version of the question now changed to finding the sine 2x. No problem. So let's try to find it. Well, I got the sine 2x, my friend. What encourages you is to use the double angle, isn't it? So then I use the double angle of sine on this problem here. -2 sine x cosine x. So that is lovely, right? And then now I got to get the information from another right angle triangle. Well, this was a right angle. I got the x there. That means I can use now what? Opposite over adjacent. So it's going to be tangent. So tangent x, my friend, is given as 1/3. Then from this you can find the sine and cosine, isn't it? Because I got the hypotenuse here. That's going to be square root of 10. Voila. Then it's going to be -2 times the sine will be 1/10. Cosine will be 3/10. So there you go. So then I have -6/10 becomes -3/5. So please remember, as soon as you see right angle, it's very likely to work with the SOHCAHTOA. However, if it's got the 90 plus something, that is to work with the complementary angle, and do not hesitate. Do not hesitate to convert around, okay? That is great. Okay, so this is another very popular problem. The 3D shape, the 3D shape of this is very popular in the exam. So let's read the question carefully. It says what? The angle of depression, right? So, pause the video and read it through. And it says that the 80 meters above the sea level. So I got the 80 there, right? So that's great. And then I got the angle of depression from 2ds. So from this horizontal line, I'm looking down. So that would have been, 25 degree. Then if I use the property of a parallel line, zigzag, that's going to be 25 degree. That is great. And then, the another angle of depression from B to N was 35 degrees. So the elevation is also actually going to be 35 degree here, no problem. Okay? Then I got everything ready. This typical 3D shape is very popular, my friend. I got a right angle here, right? And then whenever you look at it, what I want to remind you is that you got to use the right angle triangle. So let's call this side as A. Let's call this side as a B. Okay? So from there, you can use the ratio. So from number 1 and number 2, on number 1, what can you use? I can use a tangent 25 degree, right? It's going to be rise over run. So that's going to be 80 over A. 80 over A. That's great. So that gives you A to B, 80 over tangent 25 degree. That is great. And number 2 is what? For B, that's going to be 80 over tangent 35 degree. So that is great. So I found the A and B as actual value, right? And then if you look at the triangle underneath, right, S and X, let's have a look at the 2D shape of S, X, and triangle. And then what we are given right now is that we found the A and B, supposedly all this constant, right? If you put that in the calculator, you should be able to find it. A and B, and then we were given the angle in between them. The angle between them was a 70 degree. SXN was a 70 degree here, my friend. And you're looking for the L. And you're looking at the SAS, which I need to use cosine rule. Okay, so this is a very, very popular 3D shape, and then make sure that you're trying to use a standing right angle triangle first to get two sides on the triangle on the base. Okay, so it's got, all I got the base L squared, now it's going to be A squared plus B squared minus 2AB cosine 70 degree is going to be the equation that we need. Okay, this 3D shape is a very, very popular, so make sure you work with them. Okay, let's move on to the next question. Alright, let's have a look at the next problem. Here, something with the trigonometry with the triangle. Okay, so one thing that I want you to make sure that you understand is that every time you see triangle with the three angles here of a triangle, I want you to inevitably write down that the sum is pi, right? So 180 degrees. So A plus B plus C makes it supplementary, so 180 degree. Or, you know, we keep things simpler with the radian measure, so I'm going to write in pi. Okay, that's great. So that's great. So then our aim is to show this identity here. So for the proving, either you go from the left to the right or right to the left. It's entirely up to you. for me, I like to start with the left here because I think it's easier to simplify from the summation to the product, okay? Because product is considered simpler. So I like to start with a bit nastier so that we can cancel things out or simplify things more, okay? So that's great. So that's my decision. So now I'm gonna go with this left-hand side, but you realize, my friend, that the because of this reference angle, because of this the supplementary angle, we know if I rearrange, C is gonna be pi minus A plus B. Very good. And then now I can then substitute for C on the third term there. So it's gonna be tangent, right? Pi minus A plus B is what I've got. That's great. And yes, you can use the reference angle here, isn't it? So it doesn't really matter whether the A plus B is obtuse or acute. You can always consider this as an acute, and the result will stay the same for the obtuse as well. What I'm trying to suggest here is that, so sure, I'm going to rotate by pi much on the xy plane, but subtract by the acute angle, so-called. You don't have to assume, but it's going to be the same thing. Even if you actually try to prove it for the obtuse, it's going to be the same result. In the second quadrant, only sine is positive. Tangent must come out as a negative. All right, so that's great. So if I have that, then just rearrange there. I realize that that's going to be negative, my friend, tangent A plus B. Right, so that's great. Then every time I see the sum of angles, what encourages me to use is the complementary angle. So tangent C, right, will actually come out to be negative tangent A plus B, which I can expand further using the compound angle. So it's going to be negative, what is it, tangent A, can be bothered to write all the tangent here, please forgive me writing just simplified version of a tangent with T, all right, plus tangent of a B over 1 minus tangent of A and tangent of B, right? So that's great. So I'm going to use that, I'm going to replace that on my left-hand side with this tangent C. So, okay, therefore, my left-hand side is now going to be tangent of A plus tangent of B. That is really nice. And I'm going to copy and paste all this part here, my friend. Right? So that's great. I'm going to paste it here. So that's great. And what's more exciting here is that you understand that I can put it in a fraction. So let's try to put it into the common denominator. If I did, right? If I put it into the common denominator, my friend, oh my God, it can be bothered, but let's dig in. So my common denominator will be 1 minus tangent A tangent B. So if I multiply it with the tangent A, then voila, I get the tangent of A. Let's do it. Minus tangent square of A, tangent B, very nice, plus tangent B minus tangent A, tangent square B. Oh la la. And then maybe I should resize this, okay? Let me resize it so that I can write more on the right-hand side. Technology. So then if I do minus tangent of A, minus tangent of B, putting into the common denominator is brilliant, okay? So then it's gonna be 1 minus tangent of A, tangent of B is what I've got, okay? So that's great. So then what I can do is I can cancel things out like that. Okay, and I can cancel out the tangent B just like that. That's great. Then on the numerator, what you see there, my friend, is I got the common factor with the product of a tangent A and tangent B. So let's try to factorize it. If I try to factorize the numerator with the negative, what is it? Tangent of A, tangent of B, then what do you see? It's going to be tangent of A plus tangent of B. Okay. So it's going to be who? Over 1 minus tangent of A, tangent of B. Brilliant. But here's the thing. Check this out. Negative tangent A plus tangent B over 1 minus tangent A, tangent B was in fact something that we saw before. It's exactly the same as this, which actually we can rewind back into the tangent C. So then, yes, I can end up showing that this is actually the product of a tangent A, tangent B, and tangent C. Right, that's a brilliant. That is a great. So what this question does really is to choose which side you want to start with. I think it would be more difficult if you start with the product because you have to expand a lot, distribute a lot. Maybe I don't want that. And also use the reference angle, realizing that if you are given that these are the angles of a triangle, it is automatic that we are encouraged to right? The sum to be pi. So that was a very important step. Okay, and also that you are aware of this. What is it? Reference angle, complementary angle, all that jazz is important to simplify. Okay, so let's move on to the next question. So if I go to the next question, oh, okay, that's great. So it uses what? So it says a triangle ABC. I can just visualize roughly by sketching A, B, C, no problem. And then the BC is A. So anything that is opposite here is going to be put into the lowercase as a convention. So that's great. B and C like that, just lowercase to represent that as a side. And it says what BD is a perpendicular to AC. So AC, BD. So okay, voila, no problem. What I'm going to do is put the BD there, claiming that this is a perpendicular. It's not on scale. Please forgive me, okay? Please understand. So that's perpendicular. It says show that the CD. So let's highlight the CD, my friend. CD will be this one, right? Because the perpendicular foot was called D. So I'm going to call that as D here. Okay, sorry. Not in highlighter, but in pens, it's going to be D there. So that's the point D there, my friend. Okay, and then I want to show that that's a difference between B and C cosine A. And yes, I really want you to remember in the right angle triangle, if I got the hypotenuse and then I got the angle, the adjacent is going to be described as the cosine theta. And then the opposite is going to be described as the sine theta. So please remember this formula. Okay, so if I look at that, my hypotenuse being C, right, and the angle A there, my adjacent there is going to be C times cosine A, no doubt about that. That's why the CD is going to be, we're subtracting B with that small part of the adjacent from the triangle BDA, and then we see that, right? So that we can prove. Okay, make sure that you understand about this right angle triangle. Okay, hence by using the Pythagoras theorem in the triangle BCD, so on that triangle there, prove the cosine rule for the ABC. Okay, sure, why not? Let's try to use, what is it? The Pythagoras theorem on number 1. On number 1, my friend, if I call that this is H, if I call this is H, okay, and then what we just proved was a CD. Let's try to use the Pythagoras theorem there. So what I can see here is that length CD squared plus who? DB squared is equal to who? A squared by the Pythagoras theorem. That's what the question is asking me to use. And the CD you already proved, right? Which was, what is it? B minus C cosine A. If I square that, I get the B squared minus 2BC cosine A plus C squared cosine squared A. That's great. That's CD squared. I hope you see that right away. And then DB squared, maybe it's better to use a sign, isn't it? Because that was the opposite. So opposite, we use a sign, and hypotenuse was a C. So you know what I'm going to use? I'm going to use a plus. DB will be C squared sine squared A. Right? So that's great. Is equal to who? A squared, as it was given as a sign opposite to the angle A. So that's not bad. And because now I see for these two terms, using the Pythagorean identity, we know the sine squared plus cosine squared is simply 1. So this will end up being just the C squared. Okay, that's not bad, right? So now I see that the A squared is in fact B squared plus C squared minus 2BC cosine A. Oh, voila. That is indeed the cosine rule. So we actually managed to prove it. That's great. That is a brilliant. Okay? So let me just clear this because it was a proving question. So now I can use this A and B for free. Now I can use the cosine rule using the part B that we proved. Right? That's great. So now I can sketch the another angle. Well, I think it was supposed to be. Why is it ABB? I don't know. I think that must be the angle B. Let's hope that it is true. If I was an ABC, I actually have to check that. But if it was given to be 60 degree, let's say, okay, if that was given to be 60 degree. No, you know what? No. C squared. This is a C, and then what is it? This is a B, and this is A, and I wonder if that 60 degree is going to help me to find it. I think it must be ACB. Let's go with ACB here. Sorry about that. So if I do the ACB being 60 degree here, so sorry about the typo, then let's try to use the cosine rule here. If I did, it's going to be c squared is equal to, right? C squared is equal to a squared plus b squared minus 2ab cosine 60 degree. Right? So that is great. And then what you realize here, my friend, is that you understand that the cosine 60 is simply just half. So it cancels out with 2. So that is great. So now what you have here is that the c squared is equal to a squared plus b squared. And you know what? I don't think this is also true. Okay, sorry. So I think the first value, 60 here, is the correct angle. This is what it does when you have a lot of just one significant wrong answer in the typo. So if I call that as a C, I think hopefully this is gonna work. I think this is gonna work. Okay, so in that one, if I use the cosine rule for B, then it's going to be B squared. Okay, is equal to A squared plus C squared. What is it? Minus 2AC cosine 60 degree. Yeah, I think this is gonna work, sorry. So now the cosine 60 does not change, so it's gonna be half, so that's great. So cancels out with 2, okay? So then what you end up having here is, if I rearrange to the other side and try to put it in this descending order with the C, then you're gonna have C squared, yes, and then minus AC plus AC squared minus B squared is equal to 0 is the expression I get. Okay. Now you see a little tiny quadratic form, which I wish it was a factorizable, but from the look of it, I don't think it's factorizable. So what I'm going to actually use is the quadratic formula. I don't think it's factorizable, so I'm going to use the quadratic formula there. So let me just scale it down here of this image. Okay, so let me just zoom out, zoom in like that. And now I want to use, what is it? The quadratic formula on this quadratic expression for the subject of C. So then if I use a quadratic formula there, it's going to be C is equal to negative B, but in this time the coefficient of C is A, so it's going to be positive A plus minus square root of A squared minus 4, and then the coefficient of C was 1, so 1, and then the constant term here is A squared minus B squared. Yeah, that's very nice. Over 2 times the coefficient of C, which is 1, is the form that we have. Okay, so then if I try to simplify, it's going to be A plus minus square root of if I expand it, it's going to be 4B squared minus 3A squared over 2 over 2. But if you take the 2 inside of a square root, it becomes a 4. So it's going to end up being A over 2 plus minus square root of B squared minus 3 over 4 A squared is what I've got, and this is exactly what we wanted to prove. So for this one, a very nice problem with the right angle triangle, cosine rule, and then use of the quadratic formula to solve it. Okay, so many proof questions like this. Make sure you're able to prove a sine rule and cosine rule. Do not rely on the formula booklet. Know how to prove using this type of Pythagoras theorem. Okay, sure. So that's it for the question number 6. Let's move on to the next question. Alright, let's have a look at the next now, a very nice problem. Here it says the right angle triangle. Every time you have a right angle triangle, I want you to always think about 2 things. Either you use a SOHCAHTOA or use the Pythagoras theorem. And what I have here is that I have angle DAC. I'm going to call that as theta. So that is great. So I got the theta there. So that's great. And here, you could have used a sine, cosine, tangent to find the angle theta. However, obviously the hypotenuse are changing. So obviously we don't want to use it. I want to work with the line that is not changing. In this case, the adjacent is a good choice. So I'm going to call that as an x. Okay, so that's great. Then here, let's try to apply the trig ratio. So the first is going to be tangent theta. I think that's a lovely choice, which is going to be 2 over x. And then if I do tangent 2 theta, that's gonna be 5 over x. Okay, so that's great. And then what I can do is, I want to find the theta. That means you need to, get rid of the x. And what I can do is I will divide. So the x cancels out. So here on the left and right, tangent theta
over tangent 2 theta is what I've got. So that is a 2 over 5. Okay, and here tangent 2 theta is the double angle formula, so that's great. So I'm gonna use 2 tangent theta over 1 minus tangent squared theta. Okay, so I will get rid of it, so I will change it. So that's great. So this is what I have, and by using the double angle, so I can use the algebra to get rid of the factor. So let's get rid of the tangent theta just like that. So that's great. So if you rearrange the left hand side, what you end up getting here is 1 minus tangent squared theta over 2, because it's external over the internal product, right, for the ratio, is equal to 2 over 5. So that is great. So then you can solve for tangent. So here, if you rearrange around and try to solve the equation, what you end up getting is a tangent squared theta is a 1 over 5. So from the solving equation, I can see that the tangent theta is going to be plus minus 1 over square root of 5. So that is lovely. And here, however, we have a theta being acute. So you can then rest assured that the tangent should come out as a positive 1 over square root of 5. So that's great. So from here, you can solve theta to be the arctangent 1 over root 5 as an exact value. So that's how you can work, right? So you can use calculator if you want to find the three significant figure approximation, but for the exact value, yes, it's absolutely fine to use just the arctangent. Okay, let's have a look at the question number 8. It's something to do with the inequality. That is a great. And so let's have a look at the part A. So part A suggests that I have to solve inequality. So solving inequality it's all about either sign diagram or sketching. So it's a quadratic, so I think it's very simple to sketch. So I will sketch. So if I factorize, I get the k minus 4, k plus 3 is less than 0. So on the real line here, you got the x-intercept being negative 3 and 4. I got a concave up quadratic. Okay, I got a concave up quadratic. So that's great. And I'm looking at the negative region. So it's going to be k bigger than negative 3, less than 4. Is the inequality that the question wanted to solve. So I solved that. That's great. Now let's have a look at the part B. But before I read the part B, what I want you to make sure in your mind is that I'm dealing with a problem after having done some inequality from first part. So I know instantly that I have to associate with this inequality. I want to remind you that you must remember that, okay? Okay, so in my mind, I know I'm going to use an inequality, so let's jump in. It asks me to use this given condition cosine b is less than 1 over 4, for which I don't need to prove because it's given information. But here I'm looking at non-right angle triangle, so for that, maybe I would use a cosine rule because it's something to do with the cosine. But here I don't have the sign AB, so maybe I would call that as a K. Maybe I would call that as a K, why not? Okay, so if I use the cosine rule on B, cosine B is going to be K squared plus 2 squared minus 4 squared over 2 times 2 times K. So that's the cosine rule. And here I'm given cosine B is less than quarter. So that's great. So I can get rid of 2 times 2, which is 4, so that's great. So it's gonna be just a 1. And yes, K here is a length of a triangle. It must be positive. So I know the K is a positive, so even if I rearrange, the direction will be the same. So that is great. So the actual inequality that I have here is a K squared is a 4 minus 16, so that's negative 12 is less than K is what I've. Right, that's great. So let's rearrange it again. If I rearrange it again, then voila, I get the same inequality that we had before. So I can freely use the result that we already solved it before. However, yes, you're right. We had the fact that the k is a side of a triangle must be positive. So my final answer must be then k is a positive because it's the length of a triangle, and it must be less than 4 is my answer. Is this a correct answer, my friend? Very good. You're absolutely right. No, this is not a right answer because if it's a triangle, not only should I respect that it's a positive in length, but also it has to satisfy the triangular inequality. The triangular inequality states that the sum of the two smaller sides must exceed the largest side. So for the triangular inequality, I know k plus 2 must be bigger than 4. We know that. So from here, if I rearrange 2 by subtracting, k must be bigger than 4. Oops, sorry. Is there anything that I've done wrong? Is there anything that I should... Oh, sorry, I rearranged wrongly. It must be bigger than 2, sorry. So yes, it needs to satisfy the triangle inequality as well, so it actually has to be bigger than 2 is the correct answer. So make sure you're looking at a triangle, somehow working with the inequality, very likely to involve the triangle inequality, okay? Oh yes, a very lovely shape. I love this shape, okay? So I'm glad that the exam actually did ask this shape to induce a certain, a very, very significant inequality that you're going to use all the time when you're dealing with the derivative of a sine. So here, the part A asked me to get a triangle, AOP area. But you know, the triangle area is 1/2 AB sine C, where AB are the two given side and C is the included angle. So that's great. So from this pink triangle, then I can do 1/2 r squared sine theta, where AB are just the radius, right? So that's great. And if I look at the point of a tangency, which gives us the, what is it, right angle automatically. So I'm dealing with the right angle here. And then I have to find the height here so that I can do the base times height over 2. But here height, right? And I got the right angle, so it's very likely to use either SOHCAHTOA or Pythagoras theorem. But here, yes, I think we can do the SOHCAHTOA, no problem. So let's do tangent theta is equal to h over r. So if I do the rearrangement, h will be r times tangent theta. So that is great. So I like to use r times tangent theta as it is. And now I want to look at the area of the right angle triangle here. So if I try to do that, so what do I get? It's going to be 1/2 r times tangent theta. So that is equal to r squared over 2 tangent theta is the larger triangle at the point of the tangency. That's great. And then it suggests to find me this inequality, so I actually have to have 3 different shapes. I have 2 shapes. But in fact, if you look at the shape in detail, in a closer look, if you take a closer look, you realize there's a shape in the middle, which actually represents a sector. So I can actually use the sector formula from the circular measure. So we can do 1/2 r squared theta. And voila. Altogether, you can now create inequality, which is going to be, you know, that this sector is actually has a bigger than the smaller triangle, 1/2 r squared sine theta. And it must be small. It must be less than the formula from tangent. So r squared over 2 tangent theta. And I'm very happy with this inequality because I can get rid of the common factor r squared over 2. So if we simplify further, we get the sine theta is less than theta but less than tangent theta for theta in acute angle, is what we can conclude from this shape. But you know, as I've told you before, this is actually very, very important inequality that will be used for calculus. So you know, I like to extend a bit more. You know, so this question stops there, but you can actually extend more, which could potentially be used for paper 3. So what I'm saying here is that you know, because it's an acute angle, we know all the trig ratio are positive, including sine, cosine, tangent. So what I like to do on this inequality is I can divide by sine theta, right? So that's great. So what I like to do is to divide everything by sine theta. Okay, sine theta is what I have. That is great. So it's gonna be 1 theta over sine theta, and then 1 over cosine theta is what I've got. And then, you know, everything here is bigger than 1. So if you reciprocate, in fact, the direction of inequality changes. 1/cosine, if you reciprocate, which becomes cosine, will be actually smaller. Because, you know, if you compare the 2 and 3, if you reciprocate, half becomes bigger. Just like that for numbers that are bigger than 1. So the lower bound is actually going to be cosine. The upper bound, however, will be now 1. So now, if you send theta to 0, it becomes cosine 0, which becomes simply just a 1. You know, 1 is a constant, it's independent of a theta. So then you can see, the limit theta goes to 0, sine theta over theta is actually 1. Okay, so that's how you can prove the limit of the sine theta over theta, which is going to be used very often. This is a very popular limit. It's so important, we call it fundamental limit of trigonometry, that is going to be used a lot for calculus. So that's why this question was asked in the exam. Okay, so make sure that you appreciate this inequality more. Okay, that's great. Let's move on to the next problem here. So, okay, it asks me to expand, right? So we can just do the typical quadratic expression, no problem, right? So a squared plus b squared minus 2ab is what we're gonna do. So we can simply use that. So it's going to be if you do 1 3 minus 2 to the 3, so it becomes 4 minus 2 to the 3, right? So that's great. So it asked me to use, what is it, the compound angle for part B. For part B, if I do the compound angle, it's a kokosasa, right? If it's a difference inside, it's gonna be the summation outside. So cosine 60 minus 45 degree has to be, coco plus sasa with the 60 and 45. So if I plug it in, what you end up getting here is that the square root of 2 plus square root of 6 over 4 is what we have. So that's the value that you can find using the compound angle for small angle such as 15. So that's lovely here. And it asked me to find the BC. So BC, now I got the case of, what is it, SAS. So that means I can use cosine rule. Right, so that's great. So BC, if I call that as an x, so if I do, x squared will be, 2 squared plus root 2 squared minus 2 times square root of 2 times cosine 15 degree. Okay, so if I then expand and simplify, what you end up getting here is going to be 4 minus 2 to the 3. Well, hold on a sec, that was x squared, right? But from the part A, we just found that that's actually the perfect square of 1 minus square root of 3 squared. So that's great. So I can take off the square by taking a square root. So if I did, it's gonna be plus minus. Remember, if you want to move from square to the x, then you gotta consider the negative part as well. So plus minus 1 minus square root of 3 is the potential possible answer. If you go with just the positive, 1 minus root 3, but if you multiply by the negative, you get root 3 minus 1. And of course, I'm gonna, I'm gonna represent root 3 minus 1 because x was a side. It must be positive. But if you had chosen 1 minus root 3, which is gonna be negative, we don't want that. So we're gonna choose this answer for the answer. So for this one, yes, always try to make sure if it's a follow-up problem by, with the subcategory of ABC, it's very highly likely that you have to use the previous information. Okay, you have to use the previous information. And for this one, we are using that perfect square. But by taking a square root, we are using the square root of 3 minus 1. Okay, that's great. So that's question number 10. We're going to continue more in the next part. But beforehand, let me take a 5 and then come back to you.
Okay, let's have a look at the next problem. Here, right here it says that we have a triangle ABC. All right. So whenever you are solving a trigonometric equation, what I want you to do is try to visualize. All right. So just roughly speaking, just sketch the ABC. Why not? Okay. And then I will indicate all the information. It says BC is root 3. No problem. Okay. ABC is given as a theta. All right. Easy peasy, lemon squeezy. Okay. And I got the BCC. Oh, well, I think it's still a spelling error. Sorry about that. I think it's okay, let's say that it's BAC or BCA. You know what? Let's do pi over 3 here. I should have double checked. Sorry about that. And here I'm looking for, what is it? The AB. I'm looking for the AB. All right. So AB, I'm going to call that as an X. So I just indicate all the information here. All right. And then they're asking me to find the value like that. So no problem. So what we can do is that, I got the case of, what is it? ASA. And, as soon as you see the classification of a triangle, what I want you to do is to realize that I have to use a sine rule. Okay, for ASA or SSA, that's a sine rule also. But here's the thing: if it's SSA, you must realize that you need to consider it for the ambiguity, right? Ambiguous case. But if it's SAS or SSS, that's cosine rule. And for the SAA, you don't have to think about the ambiguity. Okay, so that's a relief, right? I don't have to think about the ambiguous case here. Okay, that's great. Let's use it. Then it's all about the pair of a side and its opposite angle, and I'm very happy that I got the pi over 3 there. But unfortunately, I don't have the opposite angle for the root 3 directly. But you do know that the sum of the interior angles of a triangle must add up to pi, right? So let's do that. So for that one, it should be the sum angle that will make the angle to be pi if you add them up together. So at this angle here, which is opposite to root 3, it's going to be 2 pi over 3 minus theta. Right, so that is great. So now I'm going to use a sine rule. So we are very aware of that. So all this thinking is what you really should do whenever you practice such problem, okay? All right, so then I'm going to use a sine rule here. And it's always better to put the unknown on the top. So I'm going to put the unknown on the top over the opposite angle, which is a sine pi over 3. But it's a special angle, so we know it's a root 3 over 2. No problem, okay? Should have the same ratio of the other side. So it's going to be root 3, all right, over, what is it, sine 2 pi over 3 minus theta is what we've got, right? So that, you know, if you, okay, so that's great. Okay, so that's great. So then I'm gonna rearrange again. So if I rearrange again, I'm going to maybe duplicate this. Wait, that's great. And then what I will do is simply just to rearrange that root 3 over 2 to the other side. So I'm gonna shift that to the other side like that. So that is a great, okay? And then, you know, root 3 cancels out. So I'm sorry, it's combined as a 3, as a perfect square. So that's great. And all you got to do is just to simplify the denominator, where you see that's a difference of angle, which then induces that we have to use a compound angle. Okay, then you can do the sacocosa, no problem. So it's going to be sine, what is it, 2 pi over 3 cosine theta minus cosine 2 pi over 3 times the sine theta is what I'm going to do. Okay, sacocosa with the difference is preserved. And then yes, so if you work with the special angle, I mean, so reference angle, in this case, you can induce that. All right, so easy peasy, lemon squeezy. What we have here so far is just to use the cosine rule, no problem, okay? However, the one thing that I wanted to remind is that you're able to do part B. Okay, so if you have done a calculus already, you realize, okay, so whenever the question asks about the optimization problem, such as maximum minimum, I'm very inclined to differentiate, right? But you know, you will realize if it's actually going to be painful to differentiate this using the chain rule or quotient rule, because it's got the sum of the sine and cosine in the reciprocal matter. So you know, you got to use a nasty quotient rule, for which you could do, but I don't want to. Okay, and one thing about the compound angle application for the trigonometry is a sum and difference of the sine and cosine. So for example, if I have a, let's say, you know, a sine theta plus b cosine theta, you can combine them as a one either sine or cosine. And typically, conventionally, if we have sum, we use sine because it's to directly link with the compound rule. So let me show you what I mean by that. So if I have a sum of sine and cosine, what I like to do is to claim that I can actually write it as a single sine. No problem. And for this one, I'm going to use a compound angle. So if I do so, it's going to be, what is it? R times, and I'm going to use a compound angle here, sacocosa. So it's going to be sine theta cosine alpha plus cosine theta sine alpha is what I've got. That's great. Okay. Okay, so then you can expand them and then compare the coefficient, because on the left and right you got the sine theta, cosine theta, just like that. Then, and for me, you know, what I like to do is to compare the coefficients. So I'm going to compare the A to be what, my friend? R cosine alpha, right? And then B is going to be R sine alpha is what I've got. Then what I need to do is to, you know, to solve the A and B, and typically what I typically ask you to do is to use the Pythagorean identity, right? So if you square this, my friend, if you square this, oh la la, and then add them together, what you end up getting here is the sum of a sine square and cosine square, which is a Pythagorean identity. It simply just becomes 1. Okay, so then it just becomes 1 on the right hand side. It just becomes r squared. That's a squared plus b squared. Okay, so I then realized that r is just going to be the Pythagoras theorem. So this is going to be simply just square root of r, a squared plus b squared. So that's lovely. And how do I find the alpha? Is the following. You can find the alpha by solving this simultaneous equation differently. So instead of using the Pythagorean identity, I will use something else. And let me quickly show you what I mean by that. So if I had a b over a, you know, instead of adding this perfect square, what I'm going to do is simply divide. If you divide I get, what is it? I get the tangent alpha is equal to b over a. Okay, so that's lovely. So then alpha is going to be who? Inverse tangent of b over a is how you can find the alpha and r. That is a typical application of a sum and sum of sine and cosine. And we're going to use it for the denominator here. Instead of dealing with the two terms, I can combine them. In physics, you learn it as a superposition, right? So I got the root 3 cosine theta plus sine theta. I'm going to describe it as, r times sine theta plus alpha is what I want to do. Okay, let's then compare two things, okay? Here, what I'm going to compare is a r, and we already found the formula. It was a square root of, what is it? It was a root 3 squared plus 1 squared. It becomes root, 3 plus 1, that's the square root of 4, that becomes 2. So that's lovely, okay? And then I'm going to find the alpha by using the, it was a tangent alpha. What was it? It was a coefficient of, it's a sine of a cosine, so that's going to be coefficient of a cosine being the sine, so that I'm going to do root 3 over, that will represent the cosine 1, okay? And we do know the special angle for tangent to be root 3, that's a pi over 3. So the alpha becomes pi over 3 is what I've got. So in fact, the AB can be expressed differently, my friend. So it's going to be, 3 over 2 times, the sine and theta plus pi over 3 is what I've got, right? So that is what we have, okay? That is what we have. And on this one, my friend, what I want to do here is to talk about the minimum value of this. We wanted to find the minimum of it, but it's a rational function. Only what is the denominator is changing. Only denominator is changing, right? So if you consider the fraction to be the minimum, you want to guarantee the denominator is a maximum, because you want to, if you divide a number with the largest possible number, the fraction itself will become the least, because the more you divide, the smaller it gets. Okay, it's got the decreasing behavior. All right, so that means, I would actually consider the maximum of the denominator, where the sine, we know theta plus pi over 3 will become maximum if it's a 1, right? So then inside theta plus pi over 3, I want this to be pi over 2, because that's the angle that makes the sine to be 1. So if you rearrange, it's a complementary angle, so it's going to be simply pi over 6. So as you can see, if you knew the sum of sine and cosine, you don't need these hideous ways of differentiation with the either chain or quotient. I don't want that. Okay, you can simply solve using the trigonometric equation. I think that's the spirit of this problem. Okay, let's move on to the next problem, my friend. Okay, so yeah, circular measure is a very, very important, isn't it? So whenever you're dealing with the circular measure, what I want you to remember is that you always try to draw extra radius, extra chord on your own. In this circular measure, you're going to be tested working a lot of geometry. All right. So if I actually look at the geometry of this, it says it's concentric with A, B, C being the center of a circle, and then we have to work with this shaded area. And for this one, what you want to do is to draw extra radius on your own, my friend, right? The question does not give you those radius, those chord to be sketched, to be written. It's your own will. It's your own responsibility to sketch that, all right? And here we did that, then we can deduce extra information. Here we have equilateral triangle. So that is going to be, pi over 3, because it's an equilateral triangle, right? And then if you actually take a closer look, the shape is actually made out of the two things. One equilateral triangle, and 3 times the segment is what I have, right? So that is great. So all I got to do is actually to remember those formula, right? So if I try to remind myself with the formula, right? And here the radius is given to be how much? Yeah, so it's just the radius r, no problem. So that is a side of equilateral triangle, and I want you to remember the height of the equilateral triangle will be root 3 over 2h, and then the area is root 3 over 4 r squared. Oops, sorry, not the height. Height is root 3 over 2r is what we have. Okay, so that's great. So and from there, right? So then I have the area of root 3 over 4r squared. That's great. And I want to look at the segment. How can I work with the segment? The segment here is going to be how much? Segment is going to be the difference between the sector and a triangle, right? The segment is a shape that is cut off from the sector by the triangle. Okay, so this is the segment, right? So that is the 1 over 2 r squared theta. That's the sector area formula. I'm going to subtract it from the triangle. If I have a two sides and included angle, then it's going to be 1 over 2 r squared sine theta, right? So that's great. So then I'm going to factorize by, what is it? R squared over 2 theta minus sine theta. Right, so that is the segment formula. That's lovely. And here in our case, right, so then I'm gonna do root 3 over 4 r squared. That's the area of the equilateral triangle. That's lovely. And I'm gonna have 3 times, okay, of these segment shapes. So I'm gonna multiply 3 times who? It's going to be 1 over 2 r squared, and then the angle given here is going to be pi over 3 minus sine pi over 3 is what I've got. Then sine pi over 3, my friend, is same as what? Root 3 over 2. Okay, so then if you expand and simplify and then try to factorize, you can find the information here. So all you got to do is really very important that you draw the extra line. Those lines are not sketched. Okay, so it is our responsibility to find those extra information on our own. The same thing as here. It says what? The radius center C has got the radius of 7. So what you need to really be careful here, my friend, is that you always try to draw the extra line. So I draw the extra line here. I didn't, the sketch didn't give us. You have to draw it. Okay, and then another radius at D, center at D was given to be 5. Okay, so that's great. If the length AB is 9 centimeter. Oh, okay, that's lovely. You got the chord as well, my friend. You got the chord, which was 9. Okay, and I want to find the area of a shaded region, which is actually made out of 2 segments. And I want you to realize that that is actually made out of a 2 segment, right? So all we have to do is really, every time you want to talk about the circular measure, okay, I want you to remember, please, 2 things, my friend. 2 things, if I know 2 things, I'm very confident being able to solve any questions on the circular measure, and that is the radius, right? If you got the value for the radius, that's lovely. And then the angle, right? If you have any angle to represent the sector, chord, segment, whatever, we are very happy to solve the question. So here, as you can see, as I've mentioned before, it is made out of the 2 segments. So let's have a look at the one on the right-hand side. Let's try to find the segment on the right-hand side. You know what? Maybe I will use a different color, right? So like that one, let's talk about that segment here. So that is actually made out of the sector made out of 7, and then the subtracted by triangle on the blue, right? So I need the radius, which I was given to be 7, so that's lovely. But I gotta find the angle. But that angle is actually quite easy to find because you got all the information. If you look at the triangle on the left, right? If you look at the triangle on the left, you realize that's an isosceles triangle. That, my friend, is an isosceles triangle, right? So that is a great. And that's isosceles triangle, and what I'm going to do is I'm going to bisect the angle like this. I'm going to bisect the angle like that, okay? So if that was a theta, my friend, right? If that was a theta, because of the bisector theorem, that becomes a theta over 2, which is very lovely, okay? And then, not only does it bisect the angle, it bisects the length as well because of the congruence, my friend. So 9 over 2 is what I've got there, and as you can see, voila, I can use either sine, cosine, tangent because I got the right angle triangle, but I got the hypotenuse and then the opposite, so I'm going to use a sine. That is great. So I'm going to use a sine theta over 2. Right? So that's great. So if I do the sine theta over 2, I got 9 over 2 over 7. So it becomes 9 over 14. That is great. So if you use a calculator now, I'm sure you can find the theta. No problem, right? Because you can use arc sine, and then the theta over 2 becomes arc sine over 9 over 14. Excuse me. It's got the 9 over 14. That's great. Then you can find the theta. So I found the theta, that's great. And then likewise, you can find the angle here. You can find the angle to be alpha here as well. Using the same logic, I'm going to do the isosceles triangle, use the bisector theorem, use the cosine. So supposedly, we were able to find the theta and alpha. So that is great. So then you can use the formula, right? The segment formula, my friend, was the difference between who? A sector and a triangle. So if I do for example, number 1 here, number 1 is going to be 1 over 2, 7 squared factorized by, what is it, the angle theta. So theta minus sine theta. And then number 2 is going to be 1 over 2, and this time the radius is a 5. And then the angle given here was a alpha, is what we have, okay? And then we're going to add them together. So that's what we can have. Okie dokie. So that is the circular measure. Every time you're dealing with the circular measure, please make sure that you're willing to find information about the radius and the angle. Same thing on this one. So what it says here is that these two circles with the center A and B, it's got the following information. I got the information of what 2r, where dB is the radius of r. Okay, so that's the information given, and I'm trying to find the shaded area, which is actually made out of the, if you draw the chord, I got the 2 segment here also. It's very similar. It's very similar. So then you realize, aha, I simply have to deal with what is it? The radius and then the angle. Okay, so and then the angle, they already have given us the representation. It says alpha be the measure of the angle CAV. That's the alpha here. Okay, that's very good. Then here CBD is going to be theta. Okay, so that's great. So you got the same formula here, isn't it? So if you look at the segment area number 1, segment area number 1, that's gonna be 1 over 2, and then his radius was 2r, so 2r perfect square, and then the angle there is gonna be alpha, so it's gonna be alpha minus sine alpha. Is great. Okay, so the number 2 is what? 1 over 2 times r squared, because it's the radius smaller one, but then the angle is a lot larger. That's gonna be theta minus sine theta is what I've got. And I'm going to add them together to talk about the shaded area. So that's part A, right? That is a part A. That's great. However, I like to actually talk a bit more on the part B. This is very good. This is very important for especially the AA students, because you know what? Every time I see something of a inverse sine, I feel unfamiliar. I don't feel comfortable. I don't feel familiar with that concept. So maybe I like to switch around the information a bit to make myself more familiar with the concept. Because if I see arc sine 1 over 4, I know nothing about that. I know nothing about that. But if I try to composite both sides by sine to make myself more familiar with the concept, then you can find probably the better lead to solve the problem. Because if I look at the 4 arc sine 1 over 4 and I have to show that that's the value of the alpha, I don't know, because I don't typically deal with the trig equation with the inverse sine. But here's the thing. So okay, so that information is exactly the same as alpha over 4 is equal to arc sine quarter. And then if you composite by the sine, what you realize is that on the right hand side I got the quarter only, and on the left hand side I got the sine alpha over 4. So what you need to do is this aim. This is my aim, my friend. I need to show that the sine alpha over 4 becomes a quarter. It is my aim. Okay, I didn't solve anything, but I just changed the look of the aim. It says if I divide alpha by 4 many times, I need to show that it becomes a quarter. It's equivalent. It's equivalent aim. Okay, and it tells me better clues about the problem. And the reason I'm saying that this is better is because it's actually asking me to split the alpha how many times? 4 times. It's strictly speaking, it's stating directly to me that I need to divide the alpha 4 many times. Beforehand, I didn't know about that, right? So here, that's great, because you already halved the alpha by connecting this A and B. So I need to separate it one step further. So what I'm going to do is I'm going to halven this like that. Okay, that angle here becomes alpha over 4. So if you look at the right angle triangle like that, then the angle is alpha over 4 is what I have, and here it becomes hypotenuse, so 2r, and then this becomes r. So that's lovely. Well, hold on a sec, my bad. This was r, but because of the bisector theorem, that's gonna be r over 2. Right, on that right angle triangle, I got the hypotenuse, the opposite, which I can perform the sine. So sine alpha over 4 is going to be, what is it? R over 2r cancels out, becomes a quarter. Right, so as you can see, sine becomes a quarter is the aim. That's the essence of the problem, my friend. And as you can see, for this one, I didn't know anything about that because I don't feel comfortable with this concept. But if I try to sort of make into the taste that we are more familiar, then you can see better clue. It's asking me to divide the alpha by 4 many times. Beforehand, I couldn't sketch that line, but because the aim suggests that I have to do, I will do so. So it is always important that you're trying to find the hidden lines of the problem. That's the deductive thinking, and that is the essence of the AA questions, especially for trigonometry like this. Okay. Okay, I'm gonna move into the next problem, but I'm gonna take a 5. Okay. See you in a bit. Hello friends, let's have a look at the next question. Let's have a look at the question number 15. It's a worthy problem, all right? If it's a worthy problem, what I would encourage you to do is always try to visualize, all right? So what they were saying here is that you got the rectangular, right, shape like this, right? Oh, and then gruff is tied at the corner, right? So there's G, top G here. And then what it says is that the length, so let's have a look at the dimension of the rectangle. It goes by 10 by 4. So it's a 4 here and 10 there. So that is great. And then the rope is strictly bigger than 4, and it's going to rotate around. So what we have here is that I have a rope like that, and then rotate around like this. Okay, so the part that he can move around here is number 1 by the sector. Okay, but if the rope is loose, right? If it's loose, then you can roam around in the section number 2 here as well. So in fact, the part that he can actually travel are separated by 2 parts: the sector and then the triangle. That's great. So if I look at the number 1, right? So sorry, if I look at the number 2, that's more trivial because I can use the right angle triangle, right? And for that one here, you know, the rope here was given to be A. The length was given to be A, which was strictly bigger than 4. So that's why it's sketched like that, right? And then the adjacent here, my friend, the adjacent here is going to be, what is it? The adjacent here was, it's by using the Pythagoras theorem. If the hypotenuse was A, and it's going to be square root of who? What is it? A squared minus 16 is what I've got. And so triangle number 2, by the right angle triangle, it's going to be 1/2 times 4 times square root of a squared minus 16. So that's great. And if you look at the area number 1, the sector, right? Let's try to find the sector. For that, I need two things, the radius and then the angle. And luckily, I'm given the radius to be a, so that's great. And now I need the length. I need to find the angle here, the theta, right? So for that theta there, my friend, you're looking at the right angle triangle like this. And I got the hypotenuse A, and then the length 4, and I got the theta there, my friend. No problem. So then I can use, what is it? Out of a SOHCAHTOA, I'm going to use a sine. So if I use a sine theta, you realize that's a 4 over A. So theta here is going to be arc sine 4 over A. Right? So that's the angle. So for that, the area here is going to be 1 over 2 A squared, and then the angle, what is it? Arc sine 4 over A. So that's great. So what I'm going to do is simply add them together to represent the part that this the graph can move around, right? So that's great. So that's the total area he can move around. Okay, but it says that now I want to graze exactly 1/2 of the field. The field was a rectangular, so the entire field here it will be given by the area of a rectangle, which is a 40, and that's gonna be same as a half. Right, so that's what we have, right? Then, what you can do is simplify by maybe multiplying 2 on both sides, right? So, what you end up getting here is that I can get rid of, what is it? Half, because it's a common factor, isn't it? So what I like to do is to get rid of a half, because it's a common factor. No problem. Then you can move around, what is it? 40 to the right-hand side. Then you get the 4 times square root of a squared minus 16. A squared times arc sine 4 over A as desired. Okay, so make sure one of this wordy problem, the most confusing part is to be able to actually visualize and try to practice this sort of interpretation skills. And yes, you will see some problem like this in a section B on any paper, or likely in the paper 2, because sometimes it's something to do with the use of calculator. Okay, let's have a look at the question number 16. A very wordy, but as soon as I see the triangle PQR, I like to do, sketch the PQR there, right? So let me quickly sketch the PQR. So that's great. So let me quickly sketch PQ. Oops, sorry. Let me quickly sketch the PQR like that. PQR. So that's lovely, right? So from here, what I want you to see is that the PR is supposed to be 12. Right, so that is a great. And then QR is given to be P, because it's opposite to angle P, and PQ is given to be lowercase r. And then sorry about that. The angle is supposed to be, I think it's when it's converted into the software, it makes that error with the thingy. But let's say the QP. So let's say that this was 30 degree here, okay? And then it says cosine rule to find that. So let's try to quickly use the cosine rule for that. So yeah. QRP. I think, all right, it might be, yeah, I think it's great. I think that's great. So for that one, let's use the cosine rule. So if I do that, it's going to be, it's a SAS. I got the, side and included angle. So that means we're going to use the cosine rule. So always try to classify the given information and decide what triangle rule that you want to use. And for this one, I'm going to use, P squared is equal to, it's going to be I squared plus 12 squared minus 2 r 12 cosine 30 degree. But I want you to remember cosine 30 degree is a special angle. So it's a root 3 over 2. We can present right away. So I can cancel out the 2. If you rearrange, I get the desired quadratic equation. So that's great. So make sure, in order to induce the problem, you are willing to sketch and use the right rule. So A is done. Let's have a look at the part B. Calculate 2 corresponding value of a PQ. Consider the possible length of a triangle is a QR. QR is P. QR was a P. Now you're given the P to be 8. All right, so that's great. So that, if I substitute the A with the P, it becomes a 64 if you put a perfect square on it. So it's got the r squared minus 12 root 3 are plus, you're subtracting 64 by you're subtracting by 64, so you got 80 is equal to 0. So that is great. And for that one, yes, luckily what I see is that this is the even coefficient, so I can actually use the quadratic formula. So if I do, r is going to be, it's an even coefficient, so I like to use the more simplified form. So it's gonna be 6 root 3 plus minus square root of that square, so that's a 36 times 3 minus 80 is what I've got. So that's great. So it's gonna be 6 root 3 and what is it, plus minus. So if you do that, that's 108 subtracted by 80 will be 28, righto? Yes. Okay, so I got the perfect square, which is a 4 inside, so it's going to come out as a 2. So I'm going to have a 2 root 7 are going to be the actual value. And actually both are possible, because if you look at that, that's a square root of 108, and that was a square root of 28, and obviously this is a lot bigger, so either you add or subtract, you're going to get a positive length. So it's okay to have a positive, right? Hence find the area of a smaller triangle. So what they're saying here is either you can have that information, or what is it? So what we just found was this to be 8, and then we are looking at what is it? The r to be either acute or obtuse, like that, right? Where then r would have been smaller. So as you can see, the bigger r with the acute angle will be actually a bigger triangle. So yes, r being 6 root 3 plus 2 root 7 is going to give you bigger area. So for smaller area, you want obtuse, so your r has to be smaller. So smaller area will be when, what is it? The r is 6 root 3 minus 2 root 7. And then you can use the typical area formula for the triangle, which was 1 over 2 AB sine C. So that can easily be implemented. So I would encourage you to do it. Okay. All right. So then let's have a look at the next problem here. It says that hence consider the case where P, the length QR, is not fixed to be 8. It's not fixed, my friend. It is not fixed. All right. And it says determine the range of the values of P for which is it possible to form 2 triangles. So I want 2 solutions. I want 2 solutions, my friend. If you want 2 solutions, what you can do is that, I got the quadratic expression. So what's indirectly telling me every time you see with the quadratic and 2 solution is to work with the discriminant. So this is telling me to work with the discriminant. All right, so that is great. So let's try to use a discriminant there. So then with the P not being fixed, so discriminant here is going to be, I put the little 4 in the bottom because it's got the even coefficient, so I'm going to reduce it. So it's going to be 6 root 3 perfect square minus product of the leading coefficient and the constant term, where leading coefficient was simply 1. So it's going to be 144 minus P squared. I want this to be positive because then we can have 2 solutions there, no problem. So then if you then fix it, what is it? It's gonna be 108 minus 144 plus P squared is bigger than 0. That's great. So then it's going to be P squared is bigger than what is it? The 36. Right, so that this inequality tells me then it needs to be P is less than -6, or P is bigger than 6 is what we have. So for that one, you will guarantee that your solutions are going to be, in fact, what is it? 2 roots. Okay, you are given that it's going to be 2 roots. But yeah, you're right. I think I need to make sure that these 2 roots are actually positive. I need to make sure that these 2 roots are positive. I don't know that, right? Because it can be both negative, which is then not going to be a good problem here, because then my solution R, if that is negative, then it cannot be used for the length, right? So I need to actually consider 2 things. Not only that, but also that the 2 roots are in fact positive, so that I can use it for the triangle. So let's try to see if we can find that information. So I got the first inequality using the discriminant, so no problem. And let me try to find another information using maybe the sum and product of roots. So as you are aware of, if I have a quadratic equation, right? And then I want to guarantee that the if the roots were given to be alpha and beta, then we know the sum and product formula using the Vieta's formula. So if I quickly write it down for you, a plus alpha plus beta is going to be negative b over a, and alpha plus beta is going to be c over a, right? So that's the sum and product of roots for the quadratic equation. So now if I use that sum and product formula for my quadratic here, let's try to use. So it's going to be, what is it? If those roots to be r1 plus r2, it's going to be, what is it? 12 root 3, right? That's the negative b over a. So it's going to be 12 root 3. That's great. Okay. So so for that one, so is a positive, so that's great. The sum of two roots now at the moment is positive. That does not guarantee that those two roots are positive, because one can be bigger than the other one, so that bigger than the absolute value of another negative value. So it does not guarantee that individual roots are positive. So you also need to look at the product here as well. The product here is going to be given as what? 144 minus p squared, right? So for that one, I need to make sure that is also positive, so that either both negative, both positive. But then, as you can see, sum is a positive, so product being positive will imply the individual of them positive, right? So that's great. So for that one, you realize that the p squared is less than 144, right? Yes. So that is going to be away towers to each other. So it's going to be p is bigger than negative square root of 144. That's a 12, right? So 12 is what I have. So now I'm going to, combine this inequality from what we had before. I'm going to combine this inequality from what we had using the, discriminant. So the one that we had discriminant were the following. The one that we had was the away from negative 6 to 6. So from the discriminant, if I write it in red, it was negative 6 and 6. It was away from the value, right? So that's great. But using the sum and product of roots, what we end up showing was it needs to be towers to negative 12 to 12, right? So then you realize, the desired inequality will be between negative 12 to negative 6, or 6 to 12 is the correct answer. So make sure, if you want to show that we have the possible values of p, you need to not only define that it's got two roots, but also that each solution must be positive, because we're dealing with the triangle, which deals with the physical dimension. Okay, so that's great. So that's the question number 16. Let's move on to the next problem. Oh wow, this is a very, very hard problem in my opinion. It's a very hard problem. It was one of the IB exam, I think, in 2014, possibly in November. So if you want to challenge yourself, to find a harder problem, I think anything with the 2014, either May or November papers are very difficult. So if you can actually get it done well, that means you're doing great for your IB exam preparation. Okay, so if I look at the question number, and this is very typical competition problem. So you realize you will see many competition like the AMC or UKMT or BMO problems calibrated for just the IB, right? So it's not that challenging compared to what you would have seen in the competition, because it gives you throws out more hints for you during the test. But I'm saying that it could be demanding sometimes, right? And this part A was typically difficult, very, very difficult, because it did not give you many hints. Okay, so for this one, yes, pause the video. Once you got the document, please take a look. Try to solve this problem on your own. Did you do that? So now this is solution. So for this one, what you have to realize is that I got the the sine and cosine with the same period. It's a period for that is going to be the same. And what we typically know is the sum of sine squared b and cosine squared b being 1. But at the moment, it's not in perfect square. So the spirit of this problem is that, okay, so what I like to do is to maybe square it and see if I can use the Pythagorean identity to simplify further. So let me quickly show you that. If I do the perfect square on both equations on both sides, I got the 9 sine squared b plus 24 sine b cosine c plus 16 cosine square c is equal to 36 is what I've got in the first equation. And then the second equation, it's going to be 16 sine squared c plus 24 sine c cosine b plus 9 cosine squared b is equal to 1 is what I've got, okay? That's lovely. So what I'm going to do is to add them together. So if you add them together, I got the 16, oops, sorry. I got the 16 cosine squared, 16 sine squared, right? So if you add them together, that's just a Pythagorean identity simply becoming 1, leaving the only coefficient to be 16. So that's great. And then same thing goes for the angle of B. I got the perfect square, which I can use for the Pythagorean identity. That's going to be 9. But yes, you're right. In the middle, it doesn't really cancel out anything, but other than the common factor 24. So maybe I would group by 24. Then I got the sine, cosine plus cosine sine of angle B and C and B, right? That's great. Is equal to 37. So maybe I can simplify further, right? If I add them together, that's simply 25, right? Then if I rearrange, it becomes 12. So that's great. So if I rearrange 24 again, what you end up having here is this product, sakukosa, right? Do you remember? Does it remind you anything? Very good. The sakukosa here simply becomes half because it's going to be 12 over 24. Yes, but then that one reminds us of the compound angle of a sine. That's actually the direct result from the compound angle. So I can actually end up showing sine of B plus C is the result that we have. And then this is, I think it was very hard to do because that skill hasn't been shown before in the entire history of the IB exam, and it did not give you many hints. It didn't ask you to square things out, right? Show this, hence prove this. It's a typical spirit of IB, but it was the least given. And yes, this is a very typical actually competition problem. And I think there was one problem in AMC 12 with that problem before, like in 2000, right? So you realize it was in the last 5 questions. So that was actually quite a difficult one. And what's even more difficult is part B. So this is I think this is a paper 3 level question. This is very, very challenging, I think, in my humble opinion, because again, this problem, despite this being in the section B, did not give you enough hints. We were supposed to get a lot of clues for solving challenging problems because it's all about being able to prove, learn something new and then be able to prove in the spot on the exam session. But here, it gave you the least hints. But the hints I think we were given is that we had to deal with something with the triangle giving you the 2 possible angles, right? And with the given information. And that directly deals with the sine rule, right? Because the sine rule is the only rule that could have the ambiguous case, especially the SSA, remember? Right? So SSA could have the ambiguous case, if I was given a sine of the angle and that was impaired, and if it was a B, if it was that, then we know it's going to be 2 solutions, right? So that's the condition for the ambiguous case, especially for 2 solutions, right? So, but that one did not give you to use either the sine rule or ambiguity, but it gave you the fact that the one person claimed that it's a two-angle problem. However, only the one is possible. That means you're looking at the sine rule and see if you can use that rule, right? So this is very difficult, actually, right, to think about that in the exam session. But let's have a look. So here, what it says is that, think about it. I will sketch the ABC here for you, right? Because every time you have a wordy problem, but there's a mention of a triangle, be willing to please sketch, right? And then it's got the CAB, so angle theta, right? It says that it can have 2 solutions, right? So that means for the sine rule, remember, for the ambiguous case, in order for this to have 2 solutions, either it's acute or obtuse is what we have, right? Either you can have acute or obtuse. That's the typical solutions that we have from the triangle. Okay, so that is one realization. Another thing that you need to realize is that I showed an information. So here's showed information. So you need to be willing to use that information because there's always a reason they have talked about before in the subtext category. And here, actually, we can actually find a special angle for the B plus C because the half gives you either pi over 6 or 5 pi over 6. Okay. I mean, but think about it. I'm adding 2 angles, my friend. I'm adding 2 angles. Which one is more likely to be an answer? If you think about it. Yes, you're right. But if you think about, come on, man, think about this. If B plus C was a pi over 6 in degree, that's 30 degree. B and C are very, very small angle. In fact, A will be an obtuse angle, right? But in the sine rule, my friend, when you were learning with the ambiguous case, if you could have an obtuse angle, you can surely have an acute angle because it's the first and second quadrant. But one of those questions with the ambiguous case being having only unique solution is only the acute angle. The obtuse angle did not work because if you add with one of the given angle, it exceeded the 180. So either unique solution to be right angle triangle or the acute, or two solutions with acute or obtuse. But what we're trying to here is to disprove the claim that it can have two solutions. So the incorrect answer would be the obtuse angle, because I mean, think about it. If A was obtuse, then B plus C would be pi over 6. B and C are very, very tiny value. It's more unlikely than the sum being the obtuse. Okay. So that's the spirit that you needed in the spot of the exam. So I think that was very difficult because this style of a question wasn't asked before. So I think it's very hard to think that case unless you had seen this one before from the competition sort of a practice. Okay, so what I like to do then is suppose, right? Suppose, my friend, suppose I'm going to suppose, what are you going to suppose? That theta is obtuse. That means, what is it? B plus C is going to be pi over 6. If these were the pi over 6, then you can then directly realize that B and C individually must be strictly less than pi over 6, right? They're very tiny, right? Because the sum of that is only 30 degrees. It's very, very tiny. Okay, then, and if you remember the sine function, it is, in fact, it is directly increasing from 0 to pi over 2, right? It is directly increasing up to pi over 2. Okay, so then this implies, my friend, if you look at the individual sine B and then sine C, individual value, they will be strictly less than half because their angles inputs are smaller. The output must be smaller from in the interval from 0 to pi over 2 because the sine is a directly increasing function in the interval. Okay? Okay, that's great. So the one information that you can have here now is that the sine B is actually less than half. Okay, so that's great. And yes, you know, every time you're solving a proving questions or the mathematics, is that you always should try to use the given information. So that is a given truth. It's a condition that we cannot change. It must be always true. Okay, so in that information, what it says is that the 6 is equal to 3 sine B plus 4 cosine C. Okay, so that is a great. But what we just realized is that sine B is strictly less than half, right? From our assumption that the theta is obtuse, hence the B plus C is a pi over 6. Okay, so it's going to be strictly less 3 over 2. I just replaced the sine by half. Okay, that's what I just did. And then I'm going to add by, what is it? 4 cosine C. Okay, so that's great. So let's rearrange. So if you rearrange, my friend, that's 12 over 2 for 6 to be in the fraction. So if I rearrange, that becomes subtraction. So 9 over 2 is less than 4 cosine C is what I've got. And I'm going to rearrange. So it becomes 9 over 8 is bigger than cosine C. Oh, hold on a sec. So that's the inequality that I derived. But as you can see, that's nonsense. Contradiction arises. Why is that? Because, yes, remember, the cosine function is bounded by plus minus 1. Right? It's just a radius of a circle, unit circle. And here it says that it exceeds a number that is even bigger than 1. That's a contradiction. So when I assumed a false result to be true, I fell into absurdity. That's the proof by contradiction. So that is wrong. So theta must be acute. And that's the only solution that we can have, is the sort of spirit of this problem here is. And I think this is very difficult. Again, it did not give you many footsteps for you to follow. You had to lead with the least information. Then this is more suitable for the competition problem. But it happened before, and I think that's very lovely. And it's very popular for the school test. As you can see, the teachers will love to see this type of insight from your unit test. Okay, so I want you to pay closer to look at this solution and see yourself if you can follow it well. Okay, it's a very, very lovely problem. And I'm going to move into the next problem, okay? All right, so yes, what we were talking about was that a lot of triangles, but essence of the trigonometry really relies on the identities and equations. Okay, so we're gonna have a look at many interesting problems, but beforehand, let me take a 5 and come back to you. Thank you. Okay, let's have a look at the next problem here. A very nice question because it's talking about very important thing about the trigonometry. So this is a reference angle and complementary angle. Whenever, my friend, you're dealing with the sum of the integer multiple pi, that's a reference angle. So what you just have to verify is whether it's going to be positive, negative of the same trig ratio. So here I have tangent x plus pi, and what I want you to have a look is that you're trying to draw a unit circle here, right? And then I'm sending, what is it? Pi first and add by the x, which I then land on the third quadrant, then becomes a positive tangent x, right? So because the tangent is positive in the first and third quadrant. Okay, so that's how you can verify. So for example, if I had done with the cosine x plus pi, then it would have been negative cosine x because the cosine is a negative in the third quadrant. Okay, however, you're right. If it's a sum of difference of a pi over 2 plus integer pi, then that's complementary angle. That's a complementary angle, my friend. So that you got to be careful because what you need to do is to make sure you change the ratio. So if I had a cosine x minus pi over 2, whatever, unconditionally, I'm going to convert that into sine first. Then I have to determine whether it's going to be positive or negative, my friend. But if you draw the unit circle again, I go negative pi over 2, that's a clockwise direction, but I add by the x, which then I land on the, the fourth quadrant. And in the fourth quadrant, cosine is a positive, cosine is a positive. So I have to make sure that it's a positive here. Okay, so that's how you can verify. So for that one, yes, it's gonna be, if you convert them again, so it's gonna be tangent x times, sine x. But it want everything in terms of sine and cosine, where you can then change the tangent to be sine over cosine, so it's gonna be sine squared x over cosine x is what I've got. So make sure you're comfortable with the reference angle as well as a complementary angle here, my friend. And let's have a look at this. This is an analytic trigonometric equation. It's very, very important. So what I mean by that is the following. Your input here, my friend, is an acute angle. So that goes from 0 to pi over 2. So that's great. And then you're solving the sine 2x equal to negative a. And what you might have been urged to do is to use a double angle, but I don't want you to. This is analytic trigonometric because you already have a solution. You already have a solution for sine to be a, but in this time it's a slightly changed because it's a 2x and it's a negative a. So I need to choose the quadrant well using the the reference angle. And what I want you to change, my friend, is to change the the interval of the x first. It goes from 0 to pi. So then I'm solving for the equation of 2x. So I'm going to change 2x from 0 to 2 pi. I just multiply 2 on both sides, and what you end up having here is to have a unit circle here, just a one unit circle, because that goes from 0 to 2 pi. So that's a 316 radian in degree. Okay, that's great. Then I'm solving sine to be negative a. So negative sign means the negative value for sine is in the third or fourth quadrant. And very good, because now I have a special angle B in 0 to pi over 2 that makes A, so that I can rotate him around. So I'm going to go, in order to send to the third quadrant, I'm going to go pi first and then add by A. So that's a one solution. So that's a solution number one. So we're solving for 2x at the moment. So 2x is now going to be, pi plus A, because I wanted to send to the third quadrant to make the sign value negative. Or the fourth quadrant, that's going to be 2 pi minus a. Therefore, if you rearrange, x will be pi plus a over 2, or 2 pi minus a over 2 is the solution that we have. Okay, so that's how you can find it. So make sure you don't have to work with the double angle here, and analytic trigonometric is the backbone. It's the backbone of all the trig equations, and make sure that you're aware of it. Okay. That's great. Let's have a look at this. So sure, every time you want to convert around, what is it, sine, cosine, tangent, or secant, whatever, you can use a right angle triangle, no problem. So think about this. So I'm going to just draw a right angle triangle like that. I'm going to call that as a theta. And I got the cosine, so that's going to be adjacent and hypotenuse is a piece of lemon squeezer. So I can automatically find the opposite by using the Pythagoras theorem. So that's going to be square root of 25 minus 4, so 21 is what I've got. 21, okay. How much math problem you got? a lot. Okay, so you look at this. So I have a sine, cosine to be positive, sine is negative. So that tells me the quadrant here must be in the fourth quadrant, right? Because the cosine is positive in the fourth quadrant, while sine is negative because it's below. Okay, so that you remember. So for sine, you can get the value from here. Sine theta is gonna be, what is it? Square root of 21 over 5. However, yes, it must be negative, so you just use that information, but it's not entirely the same because that assumes that this to be acute in the positive in the first quadrant, but it's acute in the fourth quadrant. Okay, so that we need to add the negative sign there. And if you look at the tangent again, I can use the ratio there. So tangent theta rise over run, so square root of 21 over 2, but negative sign in the front because it's in the fourth quadrant. Secant is a reciprocal of a cosine, so secant theta will be simply 5 over 2. So what I want you to remember is that you always respect the quadrant so that you decide whether it's going to be positive, negative on the other ratio. So let's have a look. Oh, this is very, very important. This is very, very important. For the double angle, 1 is important. For the double angle, what you typically see are the pair of a 1 with either sine or cosine. So you typically see 1 plus sine 2x or 1 plus minus cosine 2x. Well, it took plus minus here as well. Okay. So let's talk about what I mean by that. So every time you're pairing 1 with the sine, okay, what I want you to remember is that the 1 can be expressed using the, what is it, the Pythagorean identity. So that, my friend, is the same as sine squared x plus cosine squared x. Remember, 1 by the Pythagorean identity is simply just that, right? So that's great. And also, if you remember the double angle, that's, what is it, plus minus? But because I say plus minus because I got the plus minus there, 2 sine x cosine x. So as you can see, you can actually put that in the perfect square form of a sum and difference of a sine and cosine. So it's going to be sine x plus minus cosine x squared is what I've got, right? So that's the part A. Okay, so that's great. So that's lovely. So that's on the top. So that, my friend, is on the numerator, right? This is in the numerator now. Oops, that's on the numerator there. No problem. And then the double angle of cosine, there are 3 forms of it, right? But it's not in pair of 1 or minus 1. So you can use the 1 without any 1, okay, of a double angle of cosine. What is it? It is the cosine squared minus sine squared. And that's great because that's a difference of a squared, for which I can factorize further, right? So difference of a square can be expressed as what? So cosine plus sine, cosine minus sine, that's the difference of a square, isn't it? So that is lovely. So that's great. So then you can cancel things out. Well, you know, I don't have to use plus minus for that one because it was a positive in the top. So I'm going to add here. So who cancels out? Can you tell? Very good. The sum of sine and cosine cancels out once. Okay. So then on the numerator, then I see cosine plus sine over cosine minus sine. So that's a great answer. However, the question wants to describe everything in terms of a tangent. So this is a very, very typical trick. This is a very typical method that you're going to encounter many, many times. Many, many problems will eventually ask you to describe in terms of tangent in a way. So for that one, what you want to do is to choose your cosine well. Either you divide by the cosine, cosine square, cosine cubic is going to be the method. For this one, I got only the multiplicity of 1 on the top and bottom. So what I do is just to divide by the cosine once is what I'm going to do. Okay, but you got to do it on both top and bottom because essentially you are multiplying by just 1. Okay, and let's do the distribution here. So if I did, it's going to be 1 plus sine over cosine. And then on the bottom, it's going to be 1 minus sine over cosine. What's a sine over cosine? Very good, it's a tangent. So 1 plus tangent, 1 minus tangent is what I've got here. So very, very typical substitution method with the double angle of a sine with 1. Be able to put that into the perfect square is my, advice. Okay, so we proved that. So of course we want to use it, isn't it? So now if I replace the left-hand side with a 1 plus tangent over 1 minus tangent is a root 3. And then, you know, obviously you can rearrange around. If you did, you end up getting tangent is equal to 2 minus root 3. Okay. And yes, if you work on the trigonometry a lot, then you would actually realize that this is actually has a special angle to be pi over 12. All right. But you know, I don't expect you to know it at the moment. Okay. After this lesson, you will know. that it's actually pi over 12. But here's the thing, if I'm solving this equation analytically and I need to find the exact solution, what I ask you to do is the following. Yeah, you're right. I can use the inverse tangent. Why not? Let me try to use arctangent. 2 minus root 3. That's absolutely fine. This is as exact as you can get. You can leave it like that, unless the question demands you to find in the radian, in a rational multiple of pi. That we're gonna have to write in a different matter. But if I ask you to find just the exact answer plainly, then you can use arctangent, no problem. But remember, tangent is a periodic function. It can have multiple solutions, right? So from 0 to 2 pi, tangent can be positive. Well, it is a positive because the difference between 2 and 3 is just a positive. It's the first and third quadrant. So you just found the one in the first quadrant, but you gotta be able to find the one in the third quadrant. So how do you find the third quadrant? So for that inverse tangent, what I'm going to do is to add by pi. So that's another solution here. So there are two solutions there, okay? Is how we find, okay? So you can leave it like that, but I quickly just remind you, there's a special angle for that is actually pi over 12, and yes, I do want you to memorize it. Okay, it's very common to ask you to something with the tangent pi over 2, so please memorize. Tangent pi over 2 is indeed 2 minus root 3, and of course, we're going to have a look at the sine and cosine pi over 12 in the following questions, but that's the one that I would strictly remind you to memorize. And yes, in the next question, question number 22, it gives you the identity for the sine and cosine pi over 12. How lovely is that, okay? So let's have a look. So we are solving this trig equation, and yes, you know what? This was actually very hard as well. This is actually quite challenging, very hard. And in fact, this was also AMC 12 question. Okay, this was also AMC 12 question, which appeared on a very recent IB exam. I think it was a 2018, something like that, right? But it's got the spirit of AMC 12, and that's why it was typically difficult. Okay, so but luckily, so in the competition, they did not give you this identity. Okay, they did not ask you that the pi of 12 was a solution. So for the IB, they are not a competitive math. It's not a math competition. It's a high school entrance exam, so they give you a lot of hints, okay, clues. So what we need to do is to use our deductive thinking to solve it. Okay, that's great. So the first one is that I just had to verify it. What you just had to verify is just plug those values in and see it becomes 4 square root of 2, 4 times square root of 2. That's it. So we just have to verify it. So I'll leave that as an exercise for you, because just sub it in, working in thirds, right? So that you are able to multiply by the conjugate to simplify, rationalize. You do it. It's your duty. But I like to have a look at the part B, because it says find the other solution in this given domain, right? Because it's a periodic function. It's from 0 to pi over 2. Typically, it's usually one solution, but maybe the period will change if you add them together. That's what the question says, okay? So you can have actually multiple solutions from 0 to pi over 2. If it's not a clean sine or cosine, the period might have changed. So let's have a look how we can do it, okay? And here's the thing. It's very, very important. This was actually not as easy as it looks, even with these hints, because it does not tell you what to do. What we had to do is unconditionally, we had to use this information. This is given for free, so I must use it. And in fact, it does not look obvious. However, root 3 minus 1 and root 3 plus 1 is somewhat the representation of a sine pi over 12 and cosine pi over 12, because it's got the same multiple of root 2 over 4, right? So look at this. If I wanted to use this information so much, what I like to do is to multiply these two sides by, what is it? Root 2 over 4. So if I then did the distribution, if you look at the numerator, they will be replaced by sine pi over 12 and cosine pi over 12. That's great. So now I got the sine pi over 12 over sine x plus cosine pi over 12 over cosine x is what I've got. Okay, so that's great. And on the right hand side, what do I have, my friend? That's what cancels out. It becomes 2. Easy peasy. Lemon squeezy. And I don't like working with the rational form, so maybe I'll multiply by the common factor, my friend, product of sine and cosine. Let's multiply by the sine and cosine on both sides, okay? So then you have sine pi over 12 times cosine x And the cosine plus cosine times sine is a sine. So on the left-hand side, if you expand, what you get is the compound angle for sine. So what I'm going to do is simply just write sine x plus pi over 12, because that's just compound angle, sine. You can check yourself by expanding the equation on the left-hand side. All right, so that's great. Okay, and then on the right-hand side, I got the twice of the product of a sine and cosine. What does that remind you, my friend? Very good. It reminds me about the, yes, double angle of sine. It reminds me of the double angle of sine. So I'm going to write it as a sine 2x. And very, very common mistake, my friend, very, very common mistake is to claim, oh, okay, I got the trigonometric equation like this. I'm going to say 2x is simply just x plus pi over 12. Hence, the answer must be pi over 12. Yes, it is a solution. Don't get me wrong, it is a solution. However, it's not the solutions, because it's a periodic function. It can have more than one solution. So we have to be very careful with that, right? It can have more than one solution. We have to be very careful with that. So what I want to remind you here is to not assume that it's going to be one-to-one, because we just saw, even though the domain was from 0 to the power of 12, the period for example, sine 2x is a pi, so you can have multiple solutions. All right. So what I want to remind you is this: you typically see, okay, this difference of a sine and cosine with the different angle, right? With the different angle, my friends. So let's have like a sine minus sine b. So for this one, we cannot use the sum of a sine and cosine that we had done previously with the compound angle, because it's got the different period. It's got the different period. You can only use the sum of sine cosine, like the simultaneous equation, as long as it's got the same period. But I got the a and b, typically they're not the same period. For this one, the period for this one is a 2 pi, this one is pi. So it's not the same. So we got to use a different one. We got to use something called the sum to product formula. You got to use a sum to product formula. And sum to product formula for the difference of a sine is given as the following. This is going to be 2 cosine a plus b over 2 sine a minus b over 2. So that, my friend, is a sum to product formula which you can derive from the compound angle. It's not in the booklet. Please make sure you learn it. Okay, it's very important. It's not in the booklet. Then this question must be attempted with this method. Okay, let's have a look. So for that one, my friend, what I then realized is that, oh, okay, so I had that equation. So if I rearrange, I got the sine 2x minus sine x plus pi over 12. Right, so that's great. I will let that to be 0. Okay, and then what you can do is to use this method. So for that one, it's going to be twice cosine, and I'm going to add the angle. So that's going to be my a, then that's going to be my b, and then divided by 2. So that will make, 3x plus pi over 12 over 2. And then sine. If you look at the difference, that's going to be x minus pi over 12 over 2 is equal to 0. Is what I've got, right? And yes, the one solution that we had was what, x being pi over 12. So that will make this to be 0, because the sine 0 typically starts with 0, pi, 2 pi, etc. And maybe I would like to use the factor with the cosine, where the first value that makes the cosine to be 0 will be when it's a pi over 2. So you want the numerator 3x plus pi over 12 to be pi, right? So then, if I, am I doing correctly? Yes, I'm doing correctly. So if I rearrange, 3x is going to be 11 pi over 12, and then if you divide by 3, x becomes 11 pi over 36 is what we have. And that's lovely, because that is in the domain that I can solve these solutions. Okay, so whenever you typically do the sum and difference of a sine and cosine with the different period, please make sure that you're going to do the sum to product, which you can induce from the compound angle that is not in the booklet. So it is very crucial that you learn the formula taking time. Okay, so yeah, don't worry. The following questions are going to have a lot of techniques like that, so we're going to practice more. But let's have a look at the next problem. Okay, so the compound angle here. So for what values of x does the fx not exist? It's asking me for this rational function not to be existing. So that means when typically the denominator is a 0. But for me, yes, what I like to do is maybe to combine them together with the common denominator. So fx is, if I put it into common denominator, that's a sine 3x cosine x minus cosine 3x. sine x. So that's great. Over what is the product of a sine and cosine. But you know what? Every time I see the product of sine and cosine, what really urges me to do is to use the double angle of a sine, right? So for that, you know what? Arbitrarily, I will just multiply by 2 here because it's from the habit, from my observation, while solving trigonometric equations that we saw, the product of a sine and cosine is very likely to do with the double angle of a sine if you simply multiply by 2. So I did that on the top and bottom, so essentially you are multiplying by just 1. I'm not changing anything. But then now simply the denominator can transform into the double angle of a sine. So I'm going to write it as a sine 2x. So that's great. And yes, I just have to be careful. I just have to be careful when the sine 2x is 0. Okay, so when the sine 2x is 0, but here's the thing, I want to remind you this very carefully. Please remember, sine theta 0 implies theta must be integer pi. Please memorize this. This is as basic and fundamental as it gets, okay? And the cosine theta being 0 means theta has to be pi over 2 plus integer pi. It is what we have. Well, where the k is also integer, right? Okay, so for that one then, it's a 0 if and only if 2x is an integer pi. So that means x, as long as it's a k pi over 2, where k is an integer, it will not exist because it makes the denominator 0, and we don't want that. Okay, that's great. And yes, we saw that it was twice of a the sine 3x cosine x minus cosine 3x times sine x over sine 2x, and then I don't want x to be integer pi over 2, then what you see here is a numerator. That's a sarcocosine, that's a compound angle of a sine. So that's going to be sine 3x minus x, which becomes a sine 2x. Boombayah. I can actually get rid of a sine 2x as it gets, and I just am left with just 2 as good as it gets. Okay, that's how you solve it. All right, so make sure you understand the zeros of a sine and cosine. Well, zeros of a tangent is going to be the same as the zeros of a sine because in the numerator of a tangent we got the sine. Okay, that's great. So let's have a look at the next problem here. So yes, this is what we talked about before. What is it? That every time, my friend, that you see something of a sine and you want to sine and cosine and you want to induce the tangent, what I ask you to do is to divide by the cosine. So when I look at this, I got the cosine plus sine over cosine minus sine. And what I want you to do is simply just, for this one, I think it would be better if I multiply by the conjugate. Should I multiply by the conjugate? Let me think. Yes, I think it would be better to multiply by the conjugate. So what I mean by that is I'm not going to divide by any cosine, but instead I'm going to multiply by the conjugate of the denominator. So that's going to be c plus s and then c plus s. Right? So if I did, on the numerator, I get the c squared plus 2 sine c plus sine squared. Over on the denominator, I see the c squared minus sine squared. And then on the denominator, what you see is that's the double angle of a cosine. That's the double angle of a cosine. So this becomes, and also, what is it? On the numerator, I got the c squared plus s squared, that's 1. And then the 2 times sine times cosine is double angle of a sine, so that's a sine 2a. So that is a great. And if you look at the c squared minus sine squared, that's a double angle of a cosine, that's just going to be cosine of a 2a. Then, if you do the, term by term division, 1 over cosine a is a secant 2a, and then the tangent 2a, sine over cosine is a tangent, so we get that. So yes, the reason I knew that I was going to multiply the conjugate is that sometimes it's better to have one term. It's better to have a single term. But here I got the difference of a sine and cosine, and maybe that did not help me to divide much. But if you multiply by the conjugate, while you have the difference of a square, you can actually convert them into a single one term as a cosine 2a. Okay, so that is why we want to make sure that we multiply the conjugate so that you can divide more quickly. Okay. That's great. So we're going to move on to the question number 25, but let me take a 5 minutes break and then come back to you. All right, let's have a look at the next question. Here, I got the sine x plus cosine x is a 2/3, right? So when you solve this problem, what I want to talk about is not how I can solve it, but how you want to really approach, right? Because my aim here is to work with the cosine 4x. Yeah, so we need to work with the cosine 4x where it's even multiple of x. So I'm sure it's something to do with the double angle, right? So you always have to remember that what is the aim. So here I got the even multiple of angle. So that means it's very likely to work with the double angle of cosine. It is to work with the double angle of a cosine. Right, I need to work with the double angle of a cosine. Okay, so let's have a look. So for that, I need to then come up with a double angle from here, where we just talked about that, for the sum of sine and cosine, we may not see, but if we square it, then I can actually work with the double angle of a sine, because I'm gonna get rid of a perfect square of a sine and cosine, them to being just 1 by the Pythagorean identity, and if it's a product of a sine and cosine, I like to work with the double angle of sine, right? So let's try to square on both sides. So that's what I'm gonna do. Okay, so that's great. So if I did, it's going to be, what is it? Sine squared plus 2 sine cosine plus cosine squared is equal to 4/9 is what I've got. So that's great, yes. And from here, sine squared plus cosine squared is simply just 1. Okay, then on the left-hand side, I got the 2 times sine times cosine is equal to negative 5/9. So that's great, yes. Then what you see here is that the product of sine and cosine, here double angle is going to be sine 2x. Okay, so that's great. So maybe I would like to use that information for the cosine 4x. And like we have mentioned before, we were already aware that it was an even multiple of angle. So I'm going to use a double angle. So let's do cosine 4x is equal to cosine 2 times 2x. So that's great. And for that one, we can apply the double angle. But, I like to, there are 3 forms of double angle of a cosine. But now I got the information about the sine. Maybe I would like to work with just the one with the sine. So here I'm going to do 1 minus 2 sine squared 2x is the double angle formula of a cosine in terms of just the sine. So then I can plug it in. It's going to be 1 minus 2 times 25/9, and if you simplify the value, it's going to be 31/81 is what I've got. Okay, so that's how we can work. So make sure that we are willing to use the double angle formula in the equation. Okay, so sure, let's move on to the next problem. Hello, my friends, let's have a look at the next problem. Here it says the double angle. Find all the solution of a tangent x plus tangent 2x is equal to 0. Whenever we see, yes, the multiple of 2, I really want to make sure that we use the double angle formula here. So let's have a look. So I got the tangent x, that is great. And then tangent 2x should be the multiple of 2. So I got the, what is it? 2 tangent x over 1 minus tangent squared x is what I've got, right? So I just used the double angle formula. And yes, maybe we want to combine them, put it into the common denominator. So what you can have here is going to be tangent x minus tangent cubic x plus 2 tangent x over 1 minus tangent squared x is what I've got, right? That's great. So on the numerator, then I can combine them as a 3 tangent minus tangent cubic over 1 minus tangent squared is equal to 0. So yes, I'm looking at just the numerator, right? Numerator to be 0. We're solving this to be equal to 0 for the fraction. So for that, I can factorize. So do not, carelessly divide, because strict ratio can be 0. So I will avoid by dividing unless I know for sure that it cannot have a 0 factor. So it's going to be t, 3 minus t squared is equal to 0. Therefore, tangent can be 0 or plus minus root 3 by solving that cubic equation. So in this given domain, then we can find the desired value. So it's a 0 closed, 360 open is what we have. Okay, so that's great. So let's have a look. So tangent x equal to 0. I have tangent x equal to 0. That means x has to be who? Oops, sorry. X has then x has to be 0, 180 degree is what I've got, right? So it's gonna be same as the 0 over sine, where it's gonna be, we said it's an integer pi or 180 degree multiple, integer multiple. So that's great. So if it's a tangent is a root 3, then it's we know the special angle, which is a pi over 3. Well, it's in degree, so let me write in degree, 60 degree. And then tangent is positive in the first and third. And then the third, you got to add by 180, so it's going to be 240 degree. That's great. If tangent is a negative root 3, then you realize, and it should be lying in the second and fourth. So we're going to go 180 minus 60, so 120 degree, or 300 degree is what we got. So we got 1, 2, 3, 4, 5, 6. So we got 6 many solutions. So make sure in the trigonometry. Oh yes, it's a 300, right? So in the trigonometric function, it's a periodic function. You can have multiple solutions, so make sure you find all of them. And for that, you need to be very careful. You need to be always be able to describe in analytic trigonometric solutions. Okay, let's have a look at 27. So here, yes, it's asking me to just, what is it? I use compound angle. It's a kokosasa. So it's going to be cosine pi over 6 cosine x minus sine pi over 6 sine x. That's lovely. So that if I use a special angle, that's going to be root 3 over 2 cosine x minus 1 over 2 sine x is what I've got. So that's part A. Okay, so for the second problem, you got the root 3 cosine x minus sine x is equal to 1. So I got the half in each side. So what I like to do is to divide by 2 like that. Right? Let's try to divide by 2 on both sides, because then on the left-hand side, I can convert that into the identity that we actually proved before. So it's actually the same. Because it's all essence of the problem solving in IB is that you always try to use the previous hints, right? So if I use that, that's gonna be cosine. Oops. So that's gonna be cosine pi over 6 plus x is equal to 1 over 2, where x was defined from 0 to 2 pi. So that's great. So if I change the domain a bit, so pi over 6 plus x has to be either, if it's a 1 over 2, we can find the special angle, right? It's going to be pi over 3, or, well, in the given domain, I can have maybe the on the fourth quadrant, which is a 5 pi over 6. Let's see if it satisfies the domain. So here, if we have a look, I think it does. Okay, give me 1 second. Yeah, it does. So that's good. So for that one, I'm gonna rearrange. If I rearrange, x will be then, what is it? The pi over 3 minus pi over 6 will be simply pi over 6, or 4 pi over 6, which is gonna be 2 pi over 3. Both of the solutions are in the domain from 0 to 2 pi. So I'm very happy. Oh, hold on a sec. No, my bad. It should be in the fourth quadrant for half. So it should be 3. Yeah, that's better. Okay, so then it's 10 pi over 6 minus pi over 6. That's 9 pi over 6. So that's a 3 pi over 2, which is in the domain, so I'm very happy. So there are 2 solutions for that. Okay, so that's great. So we found the solutions here. So we solved the A, 1, and 2. Right, so then let's have a look at part B. Well, suddenly I got the polynomial. Why not? So it might be something with the polynomial substitution for the trigonometric. Okay, so let's see. I need to show that x equal to 1 is a 0. P of 1, we can just see if it becomes a 0. That instantly means that it's a solution. So if I plug it in, it's a 2 minus 1 minus 2 plus 1. So as you can see, it cancels out. It becomes a 0. So I got the, what is it? A1, 2, so, oops, sorry. I got the A1, 2, I got the A1, 2, 3, and 4 done. Okay, so that's great. And then it says find all the solutions. So, oh, sure. So for that one, we can do the synthetic division for the polynomial, right? So if I just write down all the coefficients, 2, negative 1, negative 2, 1. So then if I put into the synthetic division here, what do I get? If I plug in 1, very good, and it's going to come down, it's going to be 2, and so I'm going to multiply by here. So if I do, it's going to be 2, 1, 1, negative 1, negative 1, 0. It's got the solution. So here it can factorize, in fact, so my polynomial will be factorized by the linear factor, and then the quadratic factor, 2x squared plus x minus 1 is equal to 0. And I like to solve that equation. So for that one, let's see if it's a factorizable. 1, 2, 1, negative 1, right? So then, the cross product will give you the positive x, so that's great. So then it can be re-expressed as the following. It's going to be x minus 1, x plus 1, 2x minus 1 is equal to 0. So that tells me that x has to be plus minus 1 or half is what I've got. Okay, so that's great. So we found all the solutions. So that's lovely. Okay, so we did the second one also. Okay, and let's have like the third. Express the sine 2 theta cosine x plus sine x in terms of only sine. So that means, what do you want to do? But first of all, I got the doubling of a sine, so which I can express as a 2 times sine times cosine, so it becomes cosine squared plus a sine squared, right? But then now I realize the, cosine squared would be 1 minus sine squared, so it's going to be 2 sine, 1 minus sine squared plus sine squared, right? So if I express that, if I expand, it's going to be 2s minus 2s cubic plus s squared is what I've got, right? So then it says, hence solve the equation here. So I'm going to solve it in the left-hand side as I have expected, just in terms of sine. And I'm going to let that to be 1 because on the equation on the right-hand side it says 1. So if you rearrange a bit, then what you end up getting is that the 2s cubic minus s squared minus 2s plus 1 is equal to 0 is the polynomial, it's the trigonometric equation that I have. But in fact, if you let s to be x, then you get the same polynomial equation for which we already know the solution of, right? So then you can easily see that the sine x, in fact, sine theta has to be either plus minus 1 or half is what I'm looking for, okay? So that's great. So now I got the domain from 0 to 2 pi. So for sine to be 1, right, then theta has to be pi over 2. If it's a negative 1, theta has to be 3 pi over 2. We found each, that's great. What about half? Then it has to be theta pi over 6. Is that it? No, because the sign is a positive in the second quadrant as well. So that's going to be 5 pi over 6 is what we have. Okay, so as you can see, we can find multiple solutions using the polynomial substitution, which the question asked us to do. So as you can see, for trigonometry, it can be combined multiple times in terms of polynomial or identity or proof questions. So please make sure you're comfortable with that. So I'm going to have a look at the question number 28. So it says, find the equation, blah, blah, expressing your answer to the nearest degree. Okay, so for this one, I would encourage you to just simply use a calculator, right? So, but here's the thing, very important, here's the thing. I don't want to be irresponsible of telling you to simply use a calculator, right? Because in the calculator, there are many, many functionality on the calculator that we have to carefully choose which command, which function we want to use. But for part A, what you realize is that it's a periodic function. For periodic function, you can have multiple solutions. So do not use NSOLVE, no NSOLVE for an equation that could potentially have multiple solutions. Please graph it. Please graph it. Okay, so that you can see multiple intercept using the function and see how many possible solutions can there be. Because if for the n-spire, no computer algebra system, you cannot have multiple solutions using the NSOLVE. It only gives you one solution. So make sure you can find multiple solutions by graphing it. So that's part A. I will probably demonstrate on my iPad later on. But right now, let's try to find the exact value of the secant on this one. Let's try to find the exact value of that. Okay. So if I look at the part B, well, it looks like a fancy equation, but if you really just let the secant squared x as a t, then you only see a quadratic equation. So, let's try to use it. So it's going to be 3t squared minus 8t plus 4 is equal to 0. I think it must be factorizable to make the solutions possible to find the exact solution. So let's have a look. So if I do 1, 3, 2, 2, minus is what I've got, right? So here t is equal to 2 or 2 over 3, where t was the secant squared x, right? That is lovely, right? That's great. So for that one, my friend, I'm looking for the secant x. So secant x has to be, plus minus square root of 2 or plus minus square root of 2 over 3, right? However, I don't want you to stop there. You got to be very careful, my friend. You got to be very careful because you need to understand not only the domain range of the right-angle trigonometry, such as SOHCAHTOA, you need to also talk about you need to be also aware of the domain range of the secant x. Because think about this. Think about this. I'm going to sketch who first? The cosine function first. Okay. I'm going to sketch the cosine function first. It looks like this. That's the cosine function, my friend. But here's the thing, on this, what I like to do is to flip it. I'm going to do cosine x, and I'm going to do 1 over cosine x. I'm going to reciprocate, okay? For that one, my friend, look at this. Yes, for the reciprocal transformation, what's very important is that you try to change the x-intercept as a vertical asymptote, like that, right? And then the maximum minimum were +1 and -1, right? And if you flip it, then then it's going to be reciprocal transformation like this. Then what you realize, really, the range, secant theta range is, what is it, from -infinity to -1, or 1 to infinity. That's what you have here. However, if you look at the value, if you look at our value here, I got the plus minus square root of 2 over 3, which is going to be in fact in between here. So that does not exist in the secant theta. I cannot accept that. Okay, so even though in the analytic equations it tells you that it's possible, if you take a closer look in terms of a function, it does not exist. So make sure after solving the trig equation with the polynomial substitution, such as the quadratic, you also have to look at the nature of a solution for the trigonometric function, whether it can exist in his range. For secant theta, it needs to be strictly less than or equal to -1 or bigger than or equal to 1. However, for that, plus minus square root of 2 over 3 is not possible to exist. Hence, I'm not going to accept that. It is how we work, okay? So not just to work on the polynomial. Make sure if it can satisfy the trigonometric equation. So let's have a look. Oh, yes. For the inverse trig, there are many identities in the right angle trigonometry, right? But for the inverse trig, I only want you to memorize 2 things. Only 2 things, my friend. What is the sum of arcsine and cosine, okay? Sum of arcsine x and the arc cosine x is pi over 2. That's number 1. And then number 2, arc tangent x plus arc tangent 1 over x is equal to pi over 2 is what we have, right? So please memorize this identity. It's not in the booklet, so it's your responsibility to be aware of this identity. Okay, be able to prove it also. But in this one, what I can do is, so if you want to prove that identity, every time you have inverse trig, it's something to do with the angle, okay? Remember, arc tangent x is just the angle in the tangent that can be only possible from negative pi over 2 pi over 2. His range is from negative pi over 2 to pi over 2. So that's great. And that's an angle. Okay, so when you see an equation like that, what I encourage you to do is simply just composite with the tangent and try to use the compound angle in between it and see if you can actually show the left-hand side is the same as the right-hand side. So if I do the compound angle of a tangent, tangent A plus tangent B over 1 minus tangent A tangent B, if I do the compound angle here, and then make sure tangent of the arctangent is simply just x, because there's a composition between the function and inverse function, and make sure that you understand what the domain of that x is going to be. It's not all real. Please be careful. Sorry. In fact, for this one, it is all real. Okay, because the domain is all real for the arctangent. Okay, it's this special case. It's not like that for the sine of arcsine x. Okay? For that one, it's all real. Okay, so but if I do, it's gonna be 1 over 2 plus 1 over 3, 1 minus 1 over 2 times 1 over 3. That's great. So then what you end up seeing is a 5 over 6 over 5 over 6. So it becomes 1. That's the left-hand side, my friend. But if you look at the right-hand side, tangent pi over 4 is indeed 1 by the special angle. So we just showed that is exactly the same. So I'm very happy. I'm very happy. And then it says hence or otherwise. It says hence or otherwise, find the reciprocal. However, because I was aware of the identity already, I can use it. Right? Because we just saw that the arctangent, we said 2 identities that we got to remember for the inverse trig. Among them, we saw the arctangent 2 plus arctangent half must be pi over 2. We know that, right? So as you can see, if you want to look at the arctangent 2, you realize that if I rearrange to the other side, I see that it's going to be, what is it? The following pi over 2 minus arctangent half. That's great. So for that one is in fact the same thing as here. For the first one, that's going to be pi over 2 minus arctangent half. That's great. And if you look at the second one, it's going to be pi over 2 minus arctangent 1 over 3. So that's great. So if you add them together, what do you get? It's going to be pi minus the sum of arctangent half and arctangent 1/3 because I factorized by -1, and you see that's pi over 4. You see that's pi over 4. So you end up realizing that's just the 3 pi over 4 is what I've got. Okay, that's great. Okay, so that is great. However, here's the thing, right? What if you want to do the compound angle instead of memorizing this formula? Why not? Let me show you. Let me show you this. Look at this. I don't know this angle. Let's call it x. I don't know it. All right? And I'm going to composite by the tangent. So if I composite both sides by the tangent, okay? Let's see it. Let's see, my friend. Let's do the compound angle here. Then it's going to be 2 plus 3 over 1 minus 2 times 3, which you end up getting 5 over -5. So it becomes -1. And it says tangent x. But look at this, my friend. When you're solving this trigonometric equation, you might have claimed that x is equal to -pi over 4, which is not wrong for the trigonometric equation itself. However, I want you to realize, yes, you got to respect the x, you got to respect the angle for the fact that it came from the arctangent of the positive input. So for that, both of them are actually sum of a positive acute angle, which then resulted in the positive obtuse angle. So I cannot claim that -pi over 4 will be actually the angle for that one. But, you know, that makes you think twice. You know what I mean? So instead, if I didn't use that formula, but I have to solve this trigonometric equation, it gives you a room to make mistake, because this, if you look at this equation alone, that's not wrong, right? It's one of the solutions. However, if you look at closer look into the given identity, arctangent of a positive input, we always give you the positive output, positive acute angle for the arctangent, because that's how the function works on the arctangent x. So that cannot possibly be the negative value is what I can say. But you need to think about that, right? Whereas if you use the identity, it's a simple substitution, you can give you the value right away. So you got to be extra careful whenever you're dealing with the inverse trig. Okay? All right, let's have a look at the question number 30, but beforehand, let me take a 5 minutes break and then come back to you. All right, let's have a look at the next problem. Here, I got the, simplifying for the value of x here, and what I want you to remember is to realize, please remember, that the, arc sine x plus arc cosine x is equal to pi over 2, right? So that's the entry that I want you to remember. So if I quickly maybe shift that to the left-hand side, right? Then I got the arc cosine square root of 15 times x is the same as pi over 2 minus arc cosine x, for which then I can convert that into, what is it? Simply same as the arc sine x using the identity that we just learned, right? So then on the left-hand side, I got the, arc cosine x. And on the right-hand side, I got the arc sine x. So for that one, what I can do is to maybe composite by the cosine and see what we get. Okay, so if I composite with the arc cosine x, I simply get, what is it? Yes, just the input, so it's going to be square root of 15 times x is what I've got. So that's lovely there, right? That's lovely. But if you look at the cosine of arc sine x, that's a bit tricky, right? And here I want you to remember this. Cosine of arc sine x is actually the same as sine of arc cosine x, which is same as square root of who? 1 minus x squared, right? So that is what we have. And from there, that's a circle equation. This is a circle equation, right? So this is a circular equation. So that's great. Okay, so please remember. And if you ask me how to derive it, no problem, because, you know, cosine theta is a square root of 1 minus sine squared theta, when theta is from 0 to pi over 2. And yes, and as you can see, that's the way we have derived. Okay, so that's great. So in fact, what you do here is a cosine of arc cosine x will be simply square root of 15x, x being outside. But on the right hand side, I got the cosine of arc sine x, which is the Pythagorean identity becomes a circle, semicircle equation. So it's got a square root of 1 minus x squared is what I've got. So that, the equation is pretty easy to solve now, right? Because as you can see, it's going to, if you square, it's going to be 15 times x squared is equal to 1 minus x squared. Okay, so that becomes a 16x squared is equal to 1. Therefore, x is equal to plus minus 1 over 4 is what I've got. Okay, so that's great. So, but here's the thing, we always want to check the domain and range of the x, right? Because if you remember the arc sine x, or arc cosine x actually, for the arc cosine x, right? One should realize the x is defined from -1 to 1. So if you have a negative 15 square root of 15x, that's between plus minus square root of 15. So it is possible to have both positive and negative. So I'm happy with that. But please, every time you're working with the equation, make sure you check with the domain. Okay, let's have a look at the next one. Let's have a look at the question number 31. And yes, one should always consider, okay, the arc sine, arc cosine, arc tangent, all this inverse trig to be an angle. So what you're looking at here is really just sum of the angle there. So that tells me that I gotta use the compound angle, right? So let's try to use compound angle here. So if I use compound angle there, then it's going to be sine of, what is it? Arc cosine 2/3. Okay, cosine of arc sine 1/4. And then what are we going to do? We're going to add the next term, but then this time I'm going to change the, what is it? The ratio. So if I change the ratio here, what do you get? It's going to be, I'm going to add, and what I'm going to do is to change the ratio here. It's going to be, what is it? Cosine and sine is what I've got, right? So that's great. And then what you end up getting here is, the first one is going to be square root of who? 1 minus 4/9 times cosine of arc sine. Again, we already have memorized the formula. It's going to be 1 minus 1/16 plus, for that one, I'm very happy because I'm combining the cosine with the arc cosine and sine with the arc sine. So it's going to be just function and inverse function. Becomes 2/3 times 1/4. I'm very happy. So for the simplification, I will leave it as an exercise. But really, considering the arc cosine, arc sine as an angle, hence thinking about using the compound angle and use the Pythagorean identity is the key for simplifying forms like that, right? So very important. So let's have a look at this. Your identity problem, spelling error. Okay, so for this one, what I want to show is to find the expression of a cosine squared x, where I was given the multiple of 4x and 2x. So that tells me that I got to reduce down the angle. So for this one, where the double angle seems to be a great choice. So if I do that, it's going to be what? If I use a double angle here, that's going to be 2a sine 2x cosine 2x. Right? For the next one, it's going to be who? Plus b sine 2x is equal to 0. So you know what? I gotta change into the multiple of 1x, but I still have a 2x. That tells me maybe I have to use double angle again. But in fact, if you do, it's gonna be quite painful, isn't it? Because I got the sine 2x, cosine 2x, sine 2x. Gotta apply all the double angle there and then distribute. It's gonna be very, very painful scenario. But that, we said what we said whenever you were working with the trig equation is that we gotta be very careful to divide, because that can be 0. For example, if you look at the common factor here, I got the sine 2x. So if I factorize by sine 2x, what I then have is a 2a times cosine 2x plus b is equal to 0. So that's great. But I can't just divide it unless I know for sure that it will be non-zero, right? But if you look at the domain, my friend, this is why it's always important that you check your domain for the trigonometric equation. If you look at the domain, my friend, sine 2x, right, in order to this to be 0, right, and x has to be either 0, pi over 2, pi, whatever, right? However, in the given domain, right, none of that is possible because, look at this, my 0 and pi over 2 are open interval that I cannot contain 0 and pi over 2, right? And pi already exceeds the pi over 2, so that's nonsense for me to claim that it's a solution, right? So that's great. So none of them is a solution. In fact, it can never be 0 in this case, in this given domain from 0 to pi over 2. And that is great because I can simply just divide this by on the right and left and right because it's non-zero anymore, right? So that's great. So then I only have to think about this equation to be 0. That's a lot more relaxing than applying the double angle 3 times here, right? Because that would have been crazy distribution. I don't want you to suffer with that, okay? So for that one, now I have cosine 2x is equal to negative b over 2a, right? So that's great, okay? And now I want to solve cosine squared x. So from the double angle of a cosine. There are three forms of double angle of a cosine, and for that one, I'm going to use 2 cosine squared x minus 1 is what I have, right? So then if I rearrange around, so it's going to be cosine squared x is going to be, what is it? 1 minus b over 2a, and then I'm going to half it, and then you're good to go, okay? So make sure you know what the question wants. And here, if there's a room for simplification using the domain, hence making the trig ratio to be non-zero, hence dividing is the key on this one. I don't want to expand distribution, the double angle 3 times and then have a crazy expansion. We don't want that, right? It's gonna take so much time. Okay, that's great. So let's have a look at the next one here. So this is another very, very important concept of the double angle. So we said that the 1 plus minus sine 2x induces the perfect square, right? The cosine x plus minus sine x, right? So that's great. But also, I want you to remember 1 plus minus cosine 2x is also very important to use the double angle with the simplification. So if you look at the showing the identity, that's essentially the half angle. That's the half angle of a tangent, all right? But for the new, so maybe I would try to prove from the left-hand side, right? For the equivalence, either you go from the left to the right or right to the left. But for that one, here I have a sine 2 theta, which I can use the only one double angle existing for him. So it's gonna be 2 sine theta and cosine theta. So that's great. However, for the double angle of a cosine, yes, you're right. I got 3 forms to substitute, right? However, I want you to always consider 1 is your enemy. Your enemy is 1. So I want to get rid of the 1 there by taking out the negative 1 from the cosine double angle. So what I mean by that is if I have a 1 plus cosine 2 theta, I can use the double angle on the cosine. So that one is going to be 1 plus. And for the double angle of a cosine, it's going to be 2 cosine squared theta minus 1. Why have I chosen that out of 3 forms of a cosine? Because it got the negative 1. You can cancel things out. Very good. So now I got that as a 2 cosine squared theta. So that is a great. So for that one, 2 cancels out, cosine cancels out. So I got the sine of a cosine, which is essentially the same as a tangent theta. So that's how you prove the, what is it, half angle of a tangent. So that's lovely. That is lovely. Okay. All right, so for that one now, hence, so every time we have a hence, we really want to use it. So for that one, I got the cotangent pi over 2, which is a reciprocal. It's not inverse. It's a reciprocal of a tangent, right? So if you plug it in, my friend, simply just a pi over 8 on the tangent here. Why not? Okay? Then I can use the half angle of a tangent. So it becomes, what is it? Sine pi over 4, which is root 2 over 2, over 1 plus cosine 2 times pi over 8 is again cosine pi over 4, which is the same as a sine pi over 4, hence square root of 2 over 2 also, right, is what I have, right? That's great. And what I can do, my friend, is to get rid of the 2 by multiplying 2 on top and bottom. So if I did, I got the square root of 2 over 2 plus root 2. So that is, my friend, the tangent pi over 8. That's lovely. But now what do I want to do? I want to now get the cotangent pi over 2, which you then need to reciprocate. So cotangent pi over 8 is going to be 2 plus root 2 over root 2 is what I've got, right? So then you can rationalize, of course, that they ask me to rationalize. So it's going to be 2 root 2 plus 2 over 2. So then you end up having root 2 plus 1. And that is a great answer, okay? You can find A and B to be just one individually. But here, what's very important is that, yes, every time you're in a pair with the 1 with the cosine double angle, you want to get rid of it by taking out the opposite side is the key here, okay? All right, let's have a look at this one. So here I got the difference of a cosine and sine being negative 5, and I want to induce the tangent somehow, okay? And maybe it's hard to work with that one first, so what are we encouraged to do? Yes, maybe I would like to, because the sum of a sine and cosine alone is difficult to convert into the tangent. So maybe what I like to do is to maybe square it, because we saw that many of the perfect square can easily be converted into the Pythagorean identity, as well as the product of a sine and cosine can be converted into the double angle of a sine. So maybe I want that. Let's try. So if I square on both sides somehow, let's see what we're gonna get. Okay, so then if I did, my friend, here it's gonna be 9 cosine squared minus 24 sine times cosine plus 16 sine squared is equal to 25. Oh la la, that's great. However, sure, I would maybe separate the 16 by what? Sum of 9 sine squared plus 7 sine squared. Maybe I would do that, my friend. Maybe I would do that because I want to use what? Yes, I want to pair this together so that I can convert them into what? You're right, the Pythagorean identity. That's a sum of sine squared, cosine squared with the coefficient 9, so it simply becomes 9. So that's what I've got. So if I simplify the equation further, now I'm left with just 7s squared minus 24 times sine times cosine. And I got the 9 there. If you bring out the 25 to the left-hand side, I got negative 16 is equal to 0. Okay, let's check. Let's double check. 7, yes. 9 minus 16, I'm very happy. Let's see if I can factorize. Is it possible to factorize? I want to know. 1, 7, and 4, 4. Yes, I'm very happy. Negative, positive. Negative 28, positive 24. You got that, right? Oh, yeah, you're right. Hold on a sec. This is not quite right because, why? Because I don't have a cosine square on 16. That was just a constant part, so there's no factorization for this one yet. Okay. What should we do to bring out the tangent on this? Okay, no problem. But here's the thing, my last resolution is maybe to try to make everything by tangent by dividing by cosine. In fact, maybe I would try to divide everything by cosine squared. Okay, maybe I would divide by everything by cosine squared and see what beautiful things can happen. The reason I divide by the cosine squared is that because if you look at the first term, I get the, 7 times tangent squared. Do you see that? Right? That's great, yes? Yes. And that, for the second one here, only cosine cancels out, so I got negative 24 tangent. Okay, that's great. If you look at the last part, that's negative 16 over cosine squared, right? Which is the same as negative 16 times the secant squared x. However, from the Pythagorean identity, secant squared is the same as who? 1 plus tangent squared. So for that one, actually, I can describe in terms of a tangent as well. So it's going to be negative 16, 1 plus tangent squared is equal to 0. Now this is really nice because now everything is in terms of a tangent. Maybe I can then perform the quadratic factorization on this one. So let's expand, my friend. If I expand, what do I get? If I just group them together and rearrange here, what you realize is that it's going to be 7t squared minus 24t minus 16 minus 16t squared is equal to 0. That's great. So then it's going to be who? Negative 9t squared minus 24t minus 16 is equal to 0. So I'm going to multiply by negative, 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 just like that. That's great. And then let's see if I can factorize further. It's going to be 3, 3, 4, 4. Kumbaya. I'm very happy that I can actually make it into perfect square. So this is going to be 3t plus 4 perfect square is equal to 0. Therefore, t is going to be who? Negative 4 over 3 is what you have. That will be the exact value. So yes, make sure if you want to describe everything in terms of tangent, your best bet is to divide by the cosine square, or cosine cubic. It usually follows the highest power of a trigonometric expression. Because I had everything in terms of sine square, I like to divide by the cosine square, so you can guarantee that you have the tangent square. Okay, so that's great. Okay, we're gonna move on to the trigonometric function. All right, let's have a look at the trigonometric function together. All right, so yes, what's very important whenever you're trying to work with the trigonometric function is that you indicate three things all together. So the amplitude and period, and then the principal axis. Right, just to quickly remind you, whenever you want to sketch, whenever you want to sketch a trigonometric function, what I really strongly encourage you is to indicate the principal axis first. So principal axis is the constant line that we get, a constant value that we're going to add the sinusoidal function. So for me, it is very obvious that the c here, when your minimum was -4 and the maximum is 2, you find their average. So principal axis, my friend, is the average between the maximum and minimum. So it's going to be max plus minimum over 2 is what we have. So now I got the 2 and -4. If you add them up, that's -2. If you halven it, that's -2 over 2. It becomes -1. So we have this principal axis at -1. So that is great. So that's my principal axis, okay? And then you think about the amplitude. So what's the amplitude? Is from this horizontal line, you go up and down, right? So the amplitude is the difference between the principal line and either maximum minimum, right? So it's a distance. So it has to be positive. So amplitude here is going to be, 3. So that is great, okay? So now I got the A and C in the function. So next thing that I have to do is to find the value B, which is the horizontal shift. But then you realize that I'm given the maximum here, and we usually have the maximum when inside of a sign is a pi over 2. So I can let the x plus b to be sorry, I would replace the x because it's given to be 3 pi over 4, and I'm gonna let that to be pi over 2, and just like that, right? So then if you rearrange, it's going to be b is equal to 4 pi over 8 minus 6 pi over 8. So that's gonna be 2 pi over 8. That's pi over 4. So that's b. So altogether, what you have here is going to be that the y is equal to 3 sine x plus pi over 4 plus the principal axis, which is -1, is a function that we have. Okay, so that's great. So let's have a look at the next question here. So what it says is that we have to consider about the sketching the function here. And then when I'm given the function like that, then yes, very first thing that I will do is always indicate the principal axis. I'm going to indicate the principal axis. So here the principal axis given to be who? You're right. Oops. If I raise that as the h, the principal axis, the horizontal value that it's given. So I'm going to indicate the 8 here, right? So I'm going to indicate the horizontal axis just like that, and I'm given the sine function. And typically the way we sketch the sine is that it needs to start from the principal axis. So it's going to start from the middle. And then as you can see, the amplitude is 4, so it goes up and down by 4. Right, so you go up, so you add by 4, which becomes 12, and you subtract by 4, which becomes 4. So I'm going to roughly just sketch the sine function like that, absolutely not a problem, right? And then indicate the maximum minimum. So here it's going to be, 12, and it's going to be 4, so that's great. But on top of that, my friend, what you also need to indicate is the period, right? So the period is the 2 pi over the coefficient of the input t, so here it's going to be pi over 6 becomes 12, right? So that's great. So to make one cycle, it goes by 12, right? But then the domain was given to be 24. So yeah, you're right. What I need to do here is that I need to duplicate this function shape here, and then sketch once more, so that it goes up to 24. So make sure that you only sketch within the given domain. It says from 0 to 24. So that's great. So then you can find the maximum minimum, right? So for the maximum minimum, for the maximum here, yes, when the inside, which was a pi t over 6, becomes pi over 2, right? Because that makes the sign to be 1, right? So then pi cancels out. So t has to be 3 is what I'm going to put. So here it's going to be 3 comma 12 is how you find the maximum. And you can easily find the minimum if you let this to be 3 pi over 2 as well. But the essence of the sketching is that you really always appreciate the principal axis. I think that's the main thing. For this one, yes, sorry, you have to use calculator for that, so I'll show you that on the iPad, okay? But if you want to simplify, okay, so yes, for this one, it is required that you use a graphic calculator. But we talked about how to simplify this, right? Because we're going to use compound angle first, right? So if you use compound angle on this, saco cosa, right? It's a compound angle, so saco cosa. So sine of arc sine x over 4 will come out just to be x over 4. That's great. And then cosine of arc cosine is going to be just 3 over 5 times, minus, but if you do the cosine of arc sine, it's a semicircle, so it's going to be square root of what? 1 minus perfect square of that, so x squared over 16 times square root of that as a 1 minus, what is it, 9 over 25. So that's how you can also simplify and then find the expression of the function. But for this one, don't worry about it. It is to really just use calculator, and I will demonstrate that on my iPad with the calculator, okay? So that's great. So let's have a look at the next one here. So it's talking about the function composition, G composite f. Okay, so that's great. So if you look at the G composite f, where my function here is given to be the sine function, and it's talking about the range, and you can sketch roughly like the principal axis here is going to be 4, right? And then the amplitude is a 3. It goes up and down. So, and then it's going to be 7 here. If you raise by 3, and then if you subtract by 3, that's going to be 1. So the range is going to be, in fact, from 1 to 7, right? So that's okay. So that's part A, right? So that's great. And then what we're given here is that G composite f over 3 pi over 20 is equal to 7. Find the next value of x greater than 3 pi over 20 for which that is going to be 7. Okay, so that's great. So what you are given here is that I got the 3 sine 2x plus pi over 5 plus 4 is equal to 7, right? So that's great. But then I want you to realize it's a periodic function. So if I sketch my sine function like that, so let me quickly duplicate that several times so that I can show you how we're going to, show you the periodic behavior. And right now, I'm going to let this to be what? Exactly 4, right? I'm going to put it as exactly 7, right? And then as you can see, if that was a solution, which was a 3 pi over 20, the next one that you're going to have is after 1 period. That's going to be after 1 period. So you should realize that the period of that function then is 2 pi over b, which is the coefficient of the x. So in this case, it's a 2 pi over 2. So the period is pi. So we simply have to add by pi, right, to go to the next value that is going to give me the periodic behavior. It repeats, right? So here, if that was a 3 pi over 20, the next one is going to be 3 pi over 20 plus pi. And the next one is going to be 3 pi over 20 plus 2 pi is what we have. So it's the periodic behavior. Okay, so that's great. We found the range. We found the the solution for that. So using the periodicity. So that's great. And then it says it's obtained by applying 4 transformation to the graph from the sine x. State what 4 transformation reps. Oh, okay. So it's talking about the function transformation. So from the sine x, right? So I like to focus on either just inside of the bracket or outside of the bracket. That does not have order. What I mean by that is you could have just described the outside first, or you can describe the inside first. It's up to you. But when you choose the side, for example, if I decide to work within the bracket, I will get rid of those first, right? Which is going to associate with the horizontal transformation. If you decide to work with the outside, that's absolutely fine also, but make sure you stick with that. Do not switch around horizontal and vertical. And for me, if I stick with the horizontal first, and for the horizontal, it's just more beneficial. It's more efficient to describe the translation first. So from the sine x, what I'm going to do here is a sine, x plus pi over 5. All right, so from there, I'm going to composite with the 2x. So 2x plus pi over 5. So we already have 2 transformation, isn't it? So the first one is horizontal shift to the left by pi over 4. Make sure that you are aware of this. And if you multiply by 2 on the domain, you actually shrink. So it actually shrinks or compresses by factor of 2 horizontally is what we would say. Okay, so it's talking about what is it? Function transformation. So that's great. And now I'm done with the horizontal. So I'm going to go with the vertical. And for the vertical, yes, you're right. it's more important. It's more important to it's important that you multiply first. So the order switches between the horizontal and vertical, meaning for the horizontal, you work with the translation first, but for the vertical, you need to work with the dilation first. You got to multiply first, my friend. So here, I'm going to multiply by 3, and then I'm going to add, quite the opposite from what we had done with the, horizontal shift. So if I paste that, right, but this time, what am I going to go? I'm going to add by 4. So then you describe the transformations. If you multiply by 3, you actually stretched, right, out by a factor of 3 vertically is what I would say. Okay, and then if you add by 4, you shift it up by 4 units. Along up it says already the direction, so it contains the vector property. So that's how you do. So we have done part D as well. So for this is a very nice problem. Not only is this associating with the trigonometric function, but also associate with the function transformation in general. Okay, so let's have a look at the next question here. It says, find me the ABC, where A, B, C are integer. Okay, so yeah, so A is to associate with the amplitude, not necessarily the amplitude, because it could have been negative, right? Amplitude is a length. So distance, so you have to put an absolute value of the coefficient of the function. B determines the period. It is not the period. We use it for the period. And C is the horizontal line. So that the principal axis. So let's have a look. So here I'm given the minimum y value to be -1, and then the maximum is 5. So 5 minus -1 over 2. The difference over 2 gives you the amplitude. So that's gonna be 3. And if you find the average over 2, that's 2, so that's a principal axis. So the amplitude is here 3, the principal axis is 2. I'm very happy. Okay, and then from maximum to minimum, that's only the half. That's the half much of the period, right? If it's a full cycle, if it's a 1 revolution, it needs to be from maximum, minimum, maximum. All right, so for this one, so from -π/4 to π/4, that goes by how much? That's a π/2. That's only half much. So the full period was a 2π/b, but half of it will give you π/b. So b has to be 2. So that's how you can, it's capital letters, but that's how you can find it. So here b has to be 2. So make sure how you can find those significant factors for the trigonometric functions, such as the amplitude, period, and then the principal axis. So that's great. So let's have a look. So for sketching that, no problem. You realize there's 2π/b is the period, which is pi. So from 0 to pi, you need to make sure that you draw the full cycle, right? Full cycle up to the pi, and it goes from -1 to 1 for the range. So A is piece of cake. Hence, sketch a separate diagram on the graph of a cosecant. Okay, so that's worthwhile looking at, right? So what I want you to realize is that cosecant is not the inverse function. It's a multiplicative inverse. It's a reciprocal, right? So it's a 1 over sine. So it's a 1 over sine 2x. So for the reciprocal transformation, we already know that the x-intercept will be actually determined as a vertical asymptote. So it's therefore important for you to indicate the x-intercept here, isn't it? So for the 2x, you shrink by a factor of 2. So you would have been pi and 2pi, but then shrink by a factor of 2 horizontally gives you pi/2. And oops, oh my bad, that's not the shape of the a sine, my bad. That was the shape of a cosine, wasn't it? Okay, so if I re-sketch, so it's going to be like that. So now I got pi/2 and pi, right? That's great. So on that, the x-intercept here, we're gonna have the vertical asymptote, like that. And then you flip it, right? Then the maximum, minimum were -1 and 1. So if you flip them, it becomes 1 as well. So I'm going to have this type of shape of the sine function. So that's the reciprocal transformation. So which we often use for the cosecant, secant, and cotangent. Okay. All right. So yeah, the maximum, minimum is going to be ±1 as well. But at the time here, it's going to be pi/4. And this is going to be 3 pi/4 for the x value, right? So that's how we indicate. Okay, so that's great. And then it's a equivalence, so then you need to be able to show whether you can move from the left to the right or right to the left. But for the proving questions for the trigonometry, it's a very tempting to use, what is it, from the nastier part, because it gives you more room to cancel things out, right? But if you have a simplified form and start from there to prove, then you might actually have to add or multiply or subtract on your own. So I think that's more complicated. So I'm going to start from the left. It says I got the tangent x plus cotangent x, where you know it's a reciprocal of a tangent. So I'm going to use 1 over tangent x here. And my aim here is to show that it's going to be twice of the cosecant of 2x. But you know, if I put it into the common denominator, I got the t squared plus 1 over t. But then you realize from the Pythagorean identity, the t squared plus 1 is a secant squared. So I'm going to have secant squared x over tangent x. So that's great. That's lovely, right? But then the secant x is, what is it, 1 over cosine squared x, right? And then the tangent reciprocal is the cosine x over sine x, isn't it? Okay, so that's great. So what you see here is that you can simplify that, right? And now you got the product of a sine and cosine. Every time we have a product of a sine and cosine with the same multiplicity, which is raised to the power of 1 on each side, it really allows us to use the double angle of a sine. So what I like to do is to multiply by 2 top and bottom. Okay, then in the denominator, I got the product of a sine and cosine with 2. So that becomes a sine double angle, doesn't it? So I got the 2 over sine 2x, which then you see, aha, that's 2 cosecant 2x. So we proved it. So that's great. Okay, and then hence, otherwise, finally, so they are asking me to sketch this, but yeah, you're right. You know what? Sketching this alone with the differentiation, it's possible, but it's just more complicated, where we could have then just convert that into what? So you now see that my aim here is to sketch the tangent 2x plus cotangent 2x, right? But then you realize, for that function, right, for part D, that will be equivalent to 2 cosecant 4x, right? So the same thing. And for me, you know, what I like to do is, okay, so I'll convert that into 2 over, what is it, sine over 4x. So, you know, for this one, then what I like to do is, at first, I'm going to sketch the function as a sine 4x over 2, and then I will try to do the reciprocal, which is going to be the y that we wanted to sketch. Okay, so it got to be in order. So if we take those order here to sketch, so let's go with the, what is it first? Let's try to sketch the sine 4x over 2, where it's got the amplitude of a plus minus half. So I got the positive half, I got the negative half, like that. So that's great. And on this, I'm going to sketch the sine 4x with the period of what? 2 pi over 4, which is a pi over 2. So it gave me the amplitude as a pi over 2, so that's lovely. So, you know, let's then try to go with what? It's going to be pi over 2. So yeah, pi over 2, like there. So I'm going to sketch the, what is it? The sine function like that. The sine, that's the half of sine 4x. That's the half of a sine 4x. With the amplitude and the period done. So that's great. And then the x-intercept here is going to be, what is it, pi over 4. Okay, that's great. Then for my original function, what I like to do is to reciprocate, right? So then the x-intercept will become now the vertical asymptote. So that's great. And then here the maximum was half. But if you flip it, the maximum, it becomes as a minimum, and it becomes y is equal to 2. Because if you flip the half, it becomes 2. And then you do the reciprocal transformation like that. And then you do the reciprocal transformation like that. Oops, like that. So that's how you sketch, right? So then, you know, your local maximum here is going to be pi over 8 comma 2. Oh, sorry, that's a local minimum because it goes decreasing, decreasing. And your local maximum here is going to be, what is it? 3 pi over 8 comma negative 2. That's a local maximum because it goes increasing, decreasing. If you ask me, oh, can maximum be smaller than the minimum? Well, yes, because it's relative. It's a local maximum, minimum. So as long as it's got the behavior of increasing to decreasing, we call it local maximum, regardless of whether it's smaller than the local minimum, right? It doesn't matter. Okay, so that's how we can solve it, you see? So that's great. So it is not to sketch from that function, but use the cosecant to convert that into cosecant. Sketch the sine first and use the reciprocal transformation is the key. So that's the part D. So that's great. Okay, let's have a look at what is it, find the solution of this equation. So I think there are several ways of doing this. I think there's a several way of doing this, okay? What I like to do here is to use the method that we just learned. What I mean by that is that, you know, we were given this beautiful identity. We were given this tangent x plus cotangent x is equal to twice of the cosecant 2x, right? So if you rearrange, this, what do you get? So here I'm given cosecant 2x, right, is equal to 3 over 2 tangent x minus 1 over 2. So that's what I'm given, right? So, and then, you know, if you multiply by 2 on the both sides, I get the 3 and 1 here, and I got the 2. And then where you realize that that's actually same as what? I can substitute that cosecant 2x with this given identity already. So what I like to do here is that it becomes, what is it? Okay, that becomes twice of. So if I had a cosecant 2x there, I can replace that. It's going to be tangent plus, oops, sorry. It was twice of a cosecant 2x, so I can just replace that as a tangent plus 1 over tangent, right? So that's the given identity here. And on the right-hand side, I had the 3t minus 1. So everything is now in terms of a tangent, and that's way better than previously given equations because now I can only work with the trig equation just in terms of one ratio. So that's very lovely. Okay, so on that, now what I'm going to do here is to make it as a polynomial by multiplying the t on both sides, where t represents the tangent x at the moment, right? So if I do so, on the left-hand side, you get the t squared plus 1. On the right-hand side, I get the 3t squared minus t. So that's great. So now I'm going to shift to the other side. So that if I do, it's going to be 2t squared minus t minus 1 is equal to 0, which you can then, you know, easily factorize. So 1 over 2, sorry, 1 and 2, 1, 1, negative plus. So it gives you, my friend, that t has to be, what is it, 1 or negative half. Okay, that t is a tangent x. But then if you check the domain, it says from 0 to pi over 2, which is the first quadrant. So it's not possible for tangent to have the negative half. So for that one, I'm going to just let the tangent x equal to 1. And for special angle, we know only pi over 4 is the solution. Okay, so that's how you can solve. So please, you know, whenever you were given the, identity, try to use it. Please try to use it. So for this one, yes, it was important that we use the value like that. Okay. Good. All right, so that was a question number 40. Let's move on to the next one. So yeah, this is also a very, very lovely problem. Here, it asks me to prove the trigonometric identity of a sine x plus 4 sine x minus 5 y is equal to that. So for that one, you can use, what is it, compound angle, sacocosa. Right, so that if you use a sacocosa, that's sine x cosine y plus cosine x sine y, isn't it? So that's the first one, right? I abbreviated the sine and cosine as a sine and s and c, right? So that's great. But then what I need to do here, my friend, is that the question asked me to, what is it, find the difference. So I only have to let the in the middle has to be negative, and then it's a product. So what I like to do is to make it as a product like that, right? So then you see it's the difference of a square, so it's going to be just simply, what is it? It's just the difference of a square. So, you know, it's going to be perfect square on each, right? So that's great. So then I got the square, I got the square, square, right? So that's great. But then, you know, the aim here is to describe everything in terms of sine. And yes, very good. What you can do here is to get rid of a cosine square y and the cosine square x by using the Pythagorean identity, because we know that's the same as what? 1 minus sine of y squared. Okay, and then that is the same as, what is it? 1 minus sine squared of x. Right, so that's what we have, and you can plug it in and simplify that. So no problem. Okay. The reason, so you know, this is always important. It's the same fashion. So what I'm saying here is, whenever you have identity, you really want to use it. See, they didn't give you for free. It's not, you know. Obviously, we have to always follow up, right? So for part B, it says I'm given this function. So for part B, I got the function fx as a product of sine x plus pi over 6 and sine x minus pi over 6. But then you realize I can actually re-express it as a perfect square. So it's going to be sine squared x minus sine squared pi over 6 as it was given before from the part A. So that's lovely. and pi over sine power of 6 is just half from the special angle, and then if you square it, that becomes a quarter. So my job is to sketch that. But if you ask me, yes, it's not, we haven't really learned how to sketch that right away, but however, it's a function transformation, so you can always induce. So for me, what's obvious is that I'm going to sketch the sine function first and then square it. Let's try to sketch the sine function first, but the domain was given from 0 to pi. Sine x has the period of 2 pi, so I'm going to sketch the sine x just like that. Right, so that's going up to pi, but you got to square it. So now the order of transformation is the following. I'm going to do sine x, and then I'm doing the sine squared x, and then I'm going to translate by 1 unit, so quarter unit down. Okay, so here I got the sine x. If you square it, but then realize that the range is supposed to be from 0 to 1. If you square that, things are getting smaller. So what we have here is that it's going to be smaller than 1. But at the exact moment of 1, it becomes 1, right? So that is a shape of a sine square. We can easily, derive that, right? Because it's squaring the numbers between 0 and 1 actually gets smaller other than 0 and 1 itself. And then I do the horizontal. Is it possible just to select this? Then I'm going to, as you have said, shift it down by a quarter. So then if I shift it down, it's going to look like that, where its range is now -1/4, and then the 3/4 because I, subtracted by 4 units down, right? Oops. Oops. Right. So, sorry. Let me sketch it again. Sorry. Yes, it was like that. Okay. So that's -1/4, and then what is it? That's -1/4, and then the positive 3/4. So that's great. So that's the value that we have. Okay. So, and then on top of that, what I want to do here is to sketch the cosecant. I gotta sketch the cosecant now. Very good. So for cosecant, it's a reciprocal. So what we have to do is just do the reciprocal transformation, right? So your x-intercept now will become the vertical asymptote. So that's great. And then your y value, which was a 3/4, will be flipped as a 4/3, which is a bigger than 1. So it's going to be above there. And then it's going to have this, sort of a smiley behavior. And then that one, -1/4, if you flip it, it becomes -4. So it gets a lot smaller. So it's a lot below, and it goes like that. And then from this graph, right, it's not a vertical asymptote. I just cut it off because the domain was given to be up to pi. From this graph, you can figure out the range, right? So the range here is going to be the gx has to be less than or equal to -4, or gx has to be, what is it? Bigger than or equal to 4/3 is how we can do. So whenever you are given the range problem, it's always wise decision to sketch. But for sketching this, what is very primarily important is that you try to prove the part A and use a sketch from the part B, because all we got to do here is just the reciprocal transformation. Okay, yeah, so that's it for the question 41. Let's move on to the next one, but let me take a 5. Thank you. All right, let's have a look at the next problem. Here it says about the modeling, right? So many modeling with the trigonometric function because it's got this periodic and sinusoidal behavior, right? And what you typically see is the Ferris wheel, right? So, and whenever you see this Ferris wheel problem, what I want you to do is just roughly sketch the function of the behavior. So what the question says is that it starts at the bottom of the wheel. So it starts at the minimum, right? So if I just try to put this in the graph, right? If I try to put this in the graph, it looks like this, right? So that is the cosine function graph, okay? So that's great. And from here, you know, I got the minimum and I got the maximum. And for circular motion, right, your radius is going to be always the amplitude. You already have the amplitude here, so that's number one. And then it says that it moves in the constant rate, so I like to figure out the period. It says the one revolution is 16 minutes. Okay, so 2 pi over b, which represents the period, is given to be 16. Therefore, b is going to be pi over 8 is what we can write. Okay, so b is a pi over 8, so that's great. But here, you know, what you see here is whenever you want to describe the sinusoidal behavior that starts at the either maximum or minimum, it's often to do with the cosine. So for here, I know that I'll actually use cosine rather than sine, because the sine starts at the principal axis, and for that I need to do the horizontal shift. It is more confusing, but for the cosine, if it starts from the minimum, I don't have to translate, right? So that's great. So here, however, yes, the typical shape of a cosine starts from the maximum, isn't it? So it starts at the minimum. That means I flipped it, I reflect it. So here it's going to be y is equal to negative 111 over 2, and I'm going to use cosine, right? And then what's going to be the amplitude? Sorry, the period was a pi over 8. Pi over 8t is what I've got. Then yes, for the principal axis, I got to do the horizontal, the vertical translation. Right now, I got the plus minus 111 over 2 for the maximum minimum, but I want to make sure that my maximum is 117, right? So that means you need to do the horizontal or the vertical translation of how much? 61.5 much. So that's how you derive the trigonometric function from the Ferris wheel. From the circular motion, make sure you try to convert that into the graph of a cosine so that it goes up and down, etc. Okay, so that's lovely. So let's have a look at the next problem here. Sure, another one here says modeling problem. I'm given this cosine function here also. So what does it say? Number of hours, blah, blah. The following diagram shows the graph of this. Okay, so what you're given right now, is that it starts at the sorry, let me sneeze. Sorry. So here, what I'm given here is that the minimum and maximum. So let's try to indicate that. So minimum was 6.25, 0.6. That's great. Then the maximum starts at where? And next high tide, so that's gonna be 12.5, 1.5 is what I've got, right? So, and then I want you to realize that it's that we are measuring after 9 o'clock, after 9 p.m. on 10th of December is what they are saying. Okay, so that's great. Then, as you can see, you know what we see here is that the the maximum, minimum, in between them is how much difference. That's 6.25 difference, isn't it? So, you know, if you had 6.25 before, it would have landed at the maximum, right? So then I can see at 0, I'm going to have another maximum, which is a 1.5 there. So that's the cosine function that I want to derive, right? That's the cosine function that I want to derive. So for that one, now I can figure out the amplitude and period. So, right, so period here is going to be 12.5, right? So 2 pi over 5 is the period, which is 12.5. That's a 25 over 2, isn't it? Oh, sorry, 2 pi over b. And that's 25 over 2, so that's great. So if you rearrange, b is going to be 4 pi over 25 is what I've got. That's b, right? And then let's have a look at the amplitude, right? So if you look at the amplitude here, I got the 1.5 and 0.6. That's a 0.9, and I'm going to halfen it, so that's 0.45. So for my function here, 0.45 cosine, and you found the coefficient of b, coefficient b, so that the period is going to be 12.5, isn't it? So I'm going to put the 4 pi over 25t, right? So that's great. And then the principal axis here will be given as what? The average between the maximum minimum, the average. So I got the 1.5 and 0.6. If you add them, that's 2.1 over 2 is what we're going to do. So 2.1 is a 21 over 10, and you divide that by 2, so that's a 21 over 20. So I'm going to add this 21 over 20, and that's the principal axis. So you can have, as you can see, the cosine function. So from the modeling, if you're given the maximum minimum, it's very likely that you can sketch the cosine function well. But of course, you can derive the sine function using the principal axis. That's ours, not a problem. Again, the very nice problem, question number 44, with the shape of Ferris wheel, right? And once if you want to derive a function, what I would strongly suggest is that you graph the function roughly. Okay, so here it starts. Where does it start? It starts at the bottom again. So it's going to start at the minimum, right? So I'm going to start at the minimum right there. It doesn't necessarily have to start at the minimum, right? So all the recent exams suggest that it starts at like here or here or here. It really depends. For that, you need to do a bit of a horizontal shift. But for this one, very lovely, very kind question says that it starts at the bottom, right? So then we can induce a cosine function again with the negative coefficient because it's reflected, right? So that's great. And here again, the radius is given as a 61, so that's gonna be automatically, the amplitude. So my function here will have negative 61 cosine right away. The reason I put the negative again, because I want to reflect it so that it starts at the minimum. Easy peasy, lemon squeezy. And it says, we need to figure out something with the period, right? So does it have any period here? Oh, sorry, it says 2.4 revolutions per every hour. Okay, and then you wanted to express the time in minutes, right? We wanted to express in minutes. So what they're saying here is a 2.4 revolution for how long? Hour. So that's 60 minutes, okay? So that means I'm going to do one revolution with how much time is what we are doing for the ratio, for that part B, so for the coefficient B. So, let me write that as a B. So then, if you do the external is equal to internal product for the ratio, 60 over 2.4, which is a 25, is going to be your B. Right, very good. So then I found the coefficient of t, so it's going to be cosine of, 25t is what I've got. So if I left my function like that, the maximum minimum would have been plus minus 61, right? However, as you can see, the minimum is a 13. So from negative 61 to make the minimum as a positive 13, you need to shift up by 74 units up. So that's what we have. That's the the trigonometric function that you can have here, where the the period now is going to be 2 pi over 25. So that's your period, right? So that's how you can figure out, right? Oh, sorry. No. I think I've done wrong. Sorry. Let's be careful. Let's be careful. Sorry. What I just got here is actually the period. It's not the coefficient B. Sorry about that. So 25 is your period, and then you want this to be 2 pi over B to find the coefficient of t. So for that one, 2 pi over 25 should be the coefficient. My bad, right? So it should be 2 pi over 25. Yeah, that's better, right? That's better. And then your period here is going to be 25, right? So that you can sketch around. So yes, the period is 25. So if they want to sketch up to 50, then all you got to do is, yes, to represent this shape once again, right? So that it's going to have 2 revolutions is how you sketch. Okay. And then the rest is just the computation. But the more emphasis I wanted to put is how to derive the function from especially the shape of a Ferris wheel, because it's very popular. And for that, I strongly encourage you to graph it on your own and then see the period and amplitude, etc. Okay, let's have a look at, oh yes, very many questions to work with the induction. So let's have a look what skills we need. And for the induction, what you typically do is sum to product formula, right? So the factor formula, right? So we're gonna remind ourselves how to do it, okay? But make sure we are comfortable with it. And for the part A of that problem is very nice because it checks your skills with the reference angle, right? So if you check sine pi before, you can evaluate on your own. However, what you can see here is that you got the sine 5 pi before. which quadrant is it, right? Sine 5 pi over 4 by the reference angle is the same as a sine pi plus pi over 4, which I sent it in the third quadrant, right? I sent it to the third quadrant. In the third quadrant, sine becomes a negative because only tangent is a positive. So that one actually cancels out. 3 pi over 4, that's in the second quadrant. Sine is still positive in the second quadrant, very good. But I have what? A fourth quadrant, which becomes a negative because in the fourth quadrant, again, by the reference angle, only cosine is positive, so that cancels out. That's great. You're only left with sine 9 pi over 4, but by the period of a sine being 2 pi, this is actually the same as a sine pi over 4, which is square root of 2 over 2. So we can easily simplify, no problem. Okay, so that's, what is it? That's part A. All right, so let's have a look at the part B. So, you know, what they're saying is to prove the identity as the equivalence of the three lines means equivalence. And, you know, we need to choose from left to the side, left or right, and then go to the other side. And the way you choose is you always try to think of the nasty part and then trying to apply the rules to simplify, right? So for me, it's obvious that we have the, what is it, the left-hand side is nastier because it's got more term, and what I'm going to do is 1 minus cosine 2x over 2 sine x is the one I'm going to start with. And for this one, what you realize is that the you know, every time we have in pair of 1 and cosine, it's really to use double angle to get rid of that 1, right? So that's what we also discussed whenever we are dealing with the double angle of sine or cosine. We really want to get rid of that 1. He's our enemy. And the enemy, right? So cosine 2x here, if I use the double angle there, it's going to be 1 minus 2 sine squared x. That's lovely. So if you cancel it out, then it gets 2 sine squared x over 2 sine x. So that's great. So it's going to cancel out, and it's got the common factor of a sine as well. So I got the sine x, easy peasy, lemon squeezy. So you get to the right hand side, and then that's great. And then the reason they have asked me is that because we wanted to use for the induction. So for the induction, there are 3 things you need to do. You need to prove the basic step, and then the induction hypothesis implies the result to prove, and then the conclusion. You need to write 3 things, right? So look at this summation here, and then we want to prove the identity as such. So I'm going to start with the basic step. So for part C, I'm going to start with the basic step, n equal to 1. And then the left-hand side here of that sum, the first term was a sine x. So that's great. And then for the right-hand side, I've got this identity. If I replace n with 1, I get the 1 minus cosine 2x over 2 sine x. So that's great, okay? And then, you know, actually we proved above that's actually the same as a sine x, right? So it actually becomes the same thing. You prove the basic step, no problem. And then the next thing we need to do is to prove the induction hypothesis implies the result to prove. So for the induction, it's actually quite nice because for the induction, you already have your goal set up. You already know the answer, but it's more emphasis on how to get there. It's the process. So for my induction hypothesis, I'm going to let the statement to be true for n equal to k. I'm assuming n equal to k true. For that, I don't need to prove because it's my assumption, right? That's my hypothesis. So here, what I'm going to say is a sum of sine x going all the way up to sine 2k minus 1x is equal to, what is it? I'm going to let that to be 1 minus cosine 2kx over 2 sine x. That's my induction hypothesis. Okay? Great. Then I'm going to go to the result to prove. So for the result to prove, you need to prove it. Right? That I cannot use for free. You need to justify how it's going to work. So for that one, on the left-hand side, right? So what we're going to do here is we're going to add one more side here. It's going to be, what is it? I'm going to add one more, so it's going to be sine 2k plus 1x is the next term. And what I need to show is RTP means the result to prove. And then for that one, if I raise the k by 1, that's 2 times bracket k plus 1. If we expand it, that becomes 2k plus 2x is what I've got. So that's our aim. We want to show that, right? So for that one, you know, what we can do is to use the induction hypothesis. You know, the essence of induction is that you always try to use the induction hypothesis. And for summation, that's quite typical because, you know, for the left-hand side, so I cannot use this statement, by the way. It's my aim. So you cannot choose both sides. You need to always start with one side. And for that one, you know, it's quite lovely because I can actually use the induction hypothesis for the first k-many terms here. So if I use the first k-many terms, which is represented by this ratio, right, I'm going to replace that. And I'm going to add that with this, with this next term, right? So that's great. Okay, so that's good. But here's the thing, for that one, now if I put into the common denominator, what I get here is a 1 minus cosine 2kx, and then plus 2 times sine 2k plus 1x times the sine x over, what is it? 2 sine x is what I've got. So that's great. Okay, but it doesn't look like the desired answer. It doesn't look like the answer that we wanted, right? So for that one, what you then need to do is to work with the, You need to work with the sum to product formula, right? So let me quickly show you what I mean by sum to product formula. Okay, but beforehand, let me just scale it down. Okay. Sure. So if I remind you what the sum to product formula here is, that the if I have for example, sine, a plus b, and if I add the compound angle of a sine, but now a minus b, it's a sacocosa, right? And then the only alternating term is the product of cosine and sine, right? Cosine of a is sine b. But if you add them together, that cancels out. So what's only gets double here, you should try yourself using the compound angle, is the twice of sine A and sine B. And that's the, for this one, it's the, I would say this is the product to sum, right? From the product, you can convert into the sum. That's product to sum, right? So that's the product to sum, right? And that's how you can induce things, right? So what we saw here, we had the case of a 2 sine A sine B, right? So that's the one that we need to convert from the product to sum. Okay, we had the product of a sine first. And for that one, what I would encourage you to do is that, for that one, what we need to do here is to work with which compound angle. Which compound angle has got the product of a sine and sine. Because for the sine compound, it's got the sine, cosine, cosine, sine. That's product of a different trig ratios, such as the sine and cosine. But for the cosine compound, it's got the product of a sine, sine, and cosine, cosine. So it is actually to work with the product to sum formula with the cosine compound. So that's how you remember things, right? So for this one, then, what I like to do is to work with the play around with the compound angle of the cosine. So I'm going to go with cosine A minus B. And I'm going to go with the cosine A plus B, right? And then as you remember, it's got the kokosasa, right? It's got the kokosasa. That's great. And if I do the sum in the left, and then here, if I, for example, subtract it, right? It's got the kokosasa plus kokosasa minus, if you add, right? The sasa cancels out, but if you subtract it, only the twice of sine of A and the sine of B remains. So that's how you do the sum product to sum formula here. If I got the product of a sine and sine, I can convert that into the difference of the sum of the cosine compound angle in this case, right? So what we had in our induction statement was that we had the twice of the sine, 2k plus 1x times the sine x. So we had that expression in our summation after putting into the common denominator. But now using this product to sum formula, what we can do here is it's going to be cosine, and then you're going to subtract the angles. It's going to be 2kx minus cosine, and then you're going to add the angles. It's going to be 2k plus 2x. So that is lovely. So that's the identity that we're going to use. Okay. So now, if we go back to the result of proof, right? In the summation, right? So if I get that, right, that's better. If I enlarge this, right? If I enlarge this, now you see that what? That yellow highlighted part can be replaced by the identity that we just discussed, right? So it's going to be the same ratio here, right? It's got the same ratio. However, in this time, what am I going to do? I'm going to get rid of that part there, but use this sum from the product, because we just derive that formula using the compound angle of a cosine. Right? So that will replace here. Right? So that's great. Okay, and let's see if there is any term canceling out. Well, Now I'm very happy that I can get rid of that. So the only thing that's left over here is going to be 1 minus cosine. It's going to be 1 minus cosine 2k plus 2x over 2 sine x is what I've got. Right? That's great. That is lovely. And in fact, if you remember, that's the result of proof, right? That's the result of proof. So assuming induction hypothesis did indeed imply the result of proof, right? But then here's the thing, after having proven those things, what I want you to do is to focus on the third step of induction, because it has to be done by three steps. So what you need to write down in your conclusion is, yes, we show that the statement is true for n equal to 1. That was a part B, right? That was a part B. And then also, what did you show? That the assuming n equal to k true implies what? N equal to k plus 1 true was also proven, right? By part C. So with these two ways, then we can say, oh, okay, therefore, by principle of mathematical induction, the statement Pn is true for n positive integer, is the conclusion that we should write. I don't want to write this conclusion again because it's very lengthy, isn't it? But for your exam, you always have to write them, right? You shouldn't just leave the statement alone after having proven the induction hypothesis implies the result of proof. The conclusion must be given. So for the induction problem, it's typically 6 to 9 marks, and I strongly encourage you that you're aware that it's actually separated by the 3 parts: the basic step, induction hypothesis implies the result of proof, and then the conclusion. So it's always the 3 categories that they're going to mark. Okay? And yes, for the trig induction, what's very typical is that they give you questions to follow up so that you can use a statement. Now, gladly, you should happily use the statement because you proved it, right? So for here, yes, I'm adding up to 2 terms, so now I'm replacing n to be 2. So the left-hand side is, in fact, it's going to be 1 minus cosine 4x over 2 sine x. So that is a great. Okay, then I'm going to let that to be cosine x like that. Okay, that's great. And then for this one now, what you realize is that I can rearrange that to the other side, so that becomes 1 minus cosine 4x is equal to 2 times sine times cosine, right? But then you realize on the right-hand side, yes, you see that it's actually becoming the sine of a 2x. That's a double angle. So that's great. And furthermore, whenever you see the cosine in pair of 1 or negative 1, it is really time for us to use the double angle so that we can get rid of it, right? That was the key. So for that one, I leave him alone, but for the double angle of a cosine, that's going to be 1 minus 2 sine squared 2x is what I've got, is equal to sine 2x. So that's great. Okay, so then on the left-hand side, that's going to be 2 sine squared 2x. And if you shift that to the left-hand side, that's minus sine 2x. Oops. That's okay, whatever. Minus sine 2x is equal to 0, right? So then that's great because now I see I got the common factor of a sine 2x. So I can factorize, and I strongly discourage you to divide unless you know for sure that it's not 0. But in the given domain, I think it could be 0, so I'll be careful with it. So if I factorize by the sine 2x, what I get here is that it's a sine 2x, and then 2 sine 2x minus 1 is equal to 0. Therefore, you have a sine 2x being 0 or half. So that's what I have, right? And then here, you got the 2x is between 0 and 2 pi, right? So for that one, for sine 2x to be 0, it has to be integer pi. So 2x being pi is the only solution that I can have in that open interval. So therefore, x must be pi over 2 is one of the solution, right? So for that one, right? And then for half, for half, 2x has to be either what? Pi over 6 or 5 pi over 6 because it's in the second quadrant. So if you rearrange, x has to be pi over 12 or 5 pi over 12 from the analytic trigonometric, doesn't it? Isn't it? So here I got two solutions and one solution for each factor of the sine 2x being half and 0. So in total, over 3 solutions must be written. Okay, so this is very, very important induction because it's very popular. But for that, really, the essence is that you always apply the product to sum formula. Product to sum formula. For us here, we saw the product of sine two times sine A and sine B, and only compound angle that has got the product of a sine and sine is a cosine compound, and that's how you can memorize things. Okay, so we're gonna have a look at the next induction problem to familiarize ourselves with such method. But let me take a 5 and come back to you. All right, let's have a look at the next question. So for this one, I want you to fasten your seatbelt, okay? So because it's going to be demanding a lot of the techniques for the trigonometry in general. So if you can solve this one well, I'm sure you can solve most of the trig identity problem, okay? So let's give our best. So for this one, it's an induction problem. So for this one, what we want to do is to start with the basic step, right? So let's go with the n equal to 1 first. Right, so if I start with the basic step from the left-hand side, what I have here is that I got the, the cosine squared theta. And then if you look at the right-hand side, what do you have, if I replace everything with 1, what I get here is a 1 over 2, 1 plus cosine 2 theta times sine theta over sine theta, right? So then what I recognize here is that I can cancel out the sine theta there, right? And then what you realize is that I got the 1 plus cosine 2 theta. And as we know, every time I see in the pair of a cosine and 1, I can use the double angle, right? So if I do, it's going to be 1 plus, so that I can get rid of the 1. And here, if I want to get rid of 1, I can do the 2 cosine squared theta minus 1. So as you can see, 1 cancels out. So you're only left with 2 cosine squared theta. Right, so that's great. So I'm going to divide that by 2 so that I can get the cosine squared theta. So I'm very good. Okay, so that's good to go. Okay, so and that's the basic step. And then the next thing you want to do here is to work with the induction hypothesis, right? So imagine, and then that result applies the result of proof. So I'm going to assume this to be true for the k, right? And then the next thing is the aim here is to prove the result to prove, right? So here RTP is going to be cosine squared theta goes all the way up to what is it? Cosine squared k theta, and I'm going to add one more term, right? I'm going to add one more term. You find it. It's going to be cosine squared k plus 1 theta is what I've got, right? So that's correct. Then I want to show that it's going to be, what is it? 1 over 2 k plus 1 plus, if I replace that with k plus 1, that's going to be cosine 2k, k plus 2, isn't it? Okay, theta times sine k plus 1 theta is what I've got, right? Over sine theta is what I have. Okay, so that's the aim, right? That's the aim. Okay, so if that's the case, right, what you realize is that I want to use the induction hypothesis on this one. So for the left-hand side, if I start with the left-hand side, then I can replace the sum up to k with the induction hypothesis. That's going to be, what is it? Oh la la, that's going to be quite a few terms, isn't it? Ha ha ha. So if I use, it's going to be 1 over 2, and then what is it? The k plus cosine k plus 1 theta sine k theta over sine theta is what I've got, right? So, but here's the thing, if you look at my answer, it's already factorized by half. So I really hope if there is any term that I can convert the cosine square so that it's got the factor of half, so that it helps me to, factorize by the multiple of half, right? So I wish there is an identity like that, and we do, right? So if you look at the cosine squared theta, yes, what we typically did is to use the Pythagorean identity that does not have factor of half. But if I use a half angle, I have 1 over 2, 1 plus cosine 2 theta. So that's a lot better, isn't it? That's a lot better. So then I can change this into the half angle formula. So if I use a half angle formula for the k plus 1 theta, it's going to be, 1 over 2, and then 1 plus cosine twice of k plus 1 theta is what I've got. Yeah, that's a lot better, isn't it? So that's great. And from there, what you can do here is I can factorize that. So I will duplicate that and then expand the bracket. So if I expand the bracket, it's going to be, so now I have that one plugged it in half, right? Because it's got the common factor of half. So that's great. So I got that, right? So that's great. So I'm gonna add this together, right? So that's better. So that's great, right? So the reason I chose particularly for the half angle formula because it's got the factor of half. Because in my answer, everything must be in the multiple of 2, and then this gives you that, right? So that's great. And then I have to combine them together. So I think it's very lovely to see k and 1 added together because in my answer, the k plus 1 is there. So that term is going to be untouched. Okay. The only thing that I have to really work on is to see if we can simplify this quotient here with this factor, right? So that we can simplify that into the desired form with the common denominator of a sign. Okay, so let's try. So here, if I try to put into the common denominator, that means I need to multiply sine theta and top and bottom. So I have a sine theta here and then sine theta there, right? So that's great. And I'm going to add them together. So if I add them together, what you see here is in the denominator, that's going to be sine theta. And I'm going to add, and then I divide that by sine theta. Right, so that's great. And then what we saw today is that whenever we have this product, as you can see, I don't see many common factor. There's no common factor here, so it's very hard to see. Okay, so maybe it's better to expand that as sum. So what we can do here is to use the product to sum formula. Maybe I would like to do the product to sum formula. Right, so if I quickly remind you, if I have a product of a cosine and sine, if I have a product of a cosine and sine, we know 2 times cosine, what is it, A and sine B is going to be, in fact, sine A plus B sine A minus B, right? So it's going to come from the compound angle of a sine. We know that because it's a product of a different trig ratio such as cosine and sine. But the order switched, right? The one that we typically know is a sine and cosine, but it's a cosine and sine. So that means I subtracted those compound angles so that only the alternating term actually gets doubled, right? So we can think about that. But as you can see, we prefer having the coefficient of 2. So what I like to do is actually multiply 2 top and bottom. So essentially, I just multiply by 1, right? But then the reason I prefer having the coefficient of 2 is so that we can easily use the product to sum formula. So that's great. So for the first one here, so that's going to be my A and that's going to be my B. So k theta and k plus 1 theta, right? So if I use the product to sum formula for the first one, that's going to be sine. And I'm going to add them together, k plus 1 theta and k theta. So if you add them together, what you end up getting here is going to be 2k plus 1 theta. Right, so that's great. And minus the difference of angles, it's going to be sine. If you subtract the k plus 1 theta by k theta, you get simply theta. So that's great. Okay, so that's what you get in the first term. And then let's try to get from the second term here. I can use the same thing, the cosine and sine. That's a product of a cosine and sine. No problem. So we're going to add that together. And then the next one is going to come out for the angle. If you add them together, if you add the angle, that's going to be, what is it? Sine. That's a 2k plus 2 plus theta. So that's a 2k plus 3 theta is what I've got. Okay, that's great. And I'm going to subtract by sine. And then if you find the difference, that was a 2k plus 1 theta. Sorry, 2k plus 2 theta minus theta will give you 2k plus 1 theta is what I've got on the top, right? So that's great. Okay, and then in the denominator, I've got the 2 sine theta. So that's lovely, right? So and let's see if there's any term canceling out. As you can see, sine 2k plus 1 theta, sine 2k plus 1 theta cancels out. Okay, so maybe I will get rid of it. Right, so that's great. So if we did, what you end up having here is simply just, what is it? You're simply, so I would get rid of that, all right? Because we saw that it's a difference or opposite sign, okay? So maybe I will put that on the next term, right? Because you can rearrange, right? So no problem. So let's see if we can simplify that. Because if you look at my aim, if you look at our aim, it's in the product, it's a multiplication, but it's now the difference. So for this one, you can do the sum to product. You can do the sum to product, right? So sum to product formula, we also saw in the trig equation part here. So for this one, it's a sum of a sign, right? Sorry, difference of a sign, which is going to lead into the product of cosine and sine like we see, but then, you can make the substitution here m and n and rearrange for a and b. You can see the formula here. So for that one, if I use this given form and then use this substitution, what you then see for the sum to product formula, it's going to be that sine m minus sine n is going to be twice of cosine m plus n over 2 sine m minus n over 2. So that's what you can see, isn't it? So that's going to be the sum to product formula. So that's great. So on that one, now what I'm going to do here is to apply to my numerator, right? So that's the given numerator. So let me try to, use the sum to product formula for this numerator right here. Okay, so if we try that, it's going to be, 2 times, okay, cosine, and I'm going to add those angles, so that makes it 2k plus 2 theta, isn't it? Sorry, 4 theta, right? So it's going to, and then it's going to be 2k plus 4 over 2 theta is what I've got, right? So that's great. Then if you see the difference, it's going to be sine, let's put the bracket here just not to confuse ourselves with the factor. And here then it's going to be, 2k plus 3 minus theta. So it's going to be 2k plus 2 theta over 2 is what I've got, right? So that's great. And then if you expand, it's going to be 2 times, cosine, and then it's going to be k plus 2 theta, okay? And for the second term, that's going to be sine, and k plus 1 theta is what I've got, right? So that's the form that we have, that's the form. And then finally, okay, so far that has been a long journey, isn't it? So for that one now, right, what we see is that we put them together, right? We put this term here and that term together, put it into the common denominator, and ended up having what? It's going to be twice. So for that one, that's the one that I'm going to replace. So for that numerator, right, is what we have derived here, right? So that numerator can be replaced by now with this fancy product. Okay, so that's great. That's fascinating. So let me duplicate that also and put it in our numerator. But that's simplifiable further because it's got the common factor of 2. So I'll get rid of that. Okay, how you like that? And then now I get rid of the 2 here, right? So, and then what you see then here is, okay, so if I erase all this, okay, the formula and all the formula that we have done, but now we want to just stick with the answer, right? So we started off, the statement Pn plus 1, sum of adding, so k plus 1. We're adding k plus 1 many terms, right? We all did that, and here we grouped them by half first, and then we already had the sum of k and 1, so that's great. Okay, and then these quotient and that, blah blah blah, simplified, we managed to come up with this quotient here in particular, right? And as you can see, that is exactly what we wanted to show for the result to prove, right? So if you compare this statement with the answer that we have written already, cosine k plus 2, sine k plus 1, sine theta is given, right? So as you can see, this question alone, this question with induction alone gives you all the, the induction, sum to product to sum, double angle, half angle formula. It summarizes everything we already have done. So this is a very, very lovely problem. I strongly encourage you to take a look at this again and solve again, right? So if you can solve that one well, you have no worries. Okay, let's have a look at this, another induction problem here. So, the basic step, let's go with the basic step. I think that's quite trivial. The first term here is cosine, and if I let n to be 1, I got the sine 2x over 2 times sine x, and yes, voila, I can see already that I got the multiple of 2, so it's going to be 2 times sine x times cosine x, which you can get rid of the sine x, so I'm left with just the cosine x. That's fine. Okay, and then let's go with the induction hypothesis implies the result proof. So if I use, cosine x, cosine 2x, and then it's going to be cosine 2 to the power of k minus 1 x times, the next term is going to be, cosine 2 to the power of k times x is what I've got on the left. Okay, on the right hand side, sine 2 to the power of k plus 1 x is what I've got, and I got 2 to the power of k plus 1 times sine x is what I got on the right hand side, right? So then on the left, what you want to do is to use the induction hypothesis, right? So induction hypothesis with the k, it's going to be, what is it? On the left hand side, it's going to be then replacing those k multiple as a sine 2 to the power of k times x over 2 to the power of k times sine x is the induction hypothesis, right? And then I have to multiply the next term, which is the cosine 2 to the power of k times x, right? And I want to show if that's going to move onto the right hand side. But as you can see, yeah, sure, you know, every time, please, every time you see the, what is it, the multiple of the sine and cosine with the same multiple and the same input, it really tells us to use the double angle of the sine. And for that, yes, as you know, we got to multiply extra 2 here, top and bottom, so that, you know, the numerator now is going to be replaced as what? You're absolutely right. So that's going to be replaced as the double angle of the sine. So it's going to be sine of 2 times 2 to the power of kx over, and then, you know, we had to multiply the denominator by 2 as well, so that it's got the multiple of 1. It's 2 to the power of k plus 1 times sine x is what I've got. So as you can see, that's the result of proof that we wanted to do, and then you can proceed the same procedure. You can do the same procedure of describing what the statement is and the conclusion is. You can mention that, right? So no problem. Okay, let's have a look at the question number 48. It's another interesting induction problem, and if you're interested in for your internal assessment, this exam question is actually derived from the Chebyshev polynomial. Chebyshev polynomial. Right, so if you're interested in with the study of trigonometry and polynomials and angular identities, such as, you know, double, triple, quadruple, and quintuple, etc., etc., it is based on these theorems. So if you're interested, you can have a look. Okay, and part A is a typical, what is it? This is a typical product to sum. This is a typical product to sum formula. So that's okay. Okay, so, you know, I will leave that as an exercise for you to solve. But if I look at the part B, right, where n is a, so I'm given the domain as positive integer, ask me to find the t1x. Okay, so if I put t1x, what you see here is a cosine of arc cosine x, and that's a function, an inverse function, which will come out to be just in x, no problem. And if I look at the second one, so t2x, as you can see, I got the cosine of, what is it, 2 times arc cosine x. And yes, I want you to always consider the inverse trig as an angle. So it's got the 2 theta. You know, you can think of it as arc cosine x as a theta. So it's got the cosine of 2 theta, which tells me that I gotta use the double angle, isn't it? So it's gonna be 2 cosine squared of, what is it, the arc cosine x. So I'm gonna duplicate that. All right, so that's great. And then, yeah, minus 1. So as you can see, I got the function composition between cosine and arc cosine. It comes out as an x. Put it into power 2, becomes x squared, so it becomes 2x squared minus 1. So that's the number 2. No problem. Okay. Okay, so that's great. So as you can see, you know, if I put 1 and 2, I got a linear and I got a quadratic. Okay, so that's a pattern, right? That does not guarantee that, you know, if you put 3, would it come out as a cubic? I don't know that. But here, what they have told me to do is to use a result in part A to show this sum of the, you know, n plus 1 and n minus 1 would turn out to be 2x times nx. So sure, let's use it. So he asked me to use the identity given here, right? So if you look at the tn plus 1, that would have been the cosine, you know, n plus 1 times arc cosine x. And then we had to add that by, what is it, tn minus 1. So here, the identity here is going to be given as n minus 1, right? So that's great. So what you see there is going to be, you know, I'm going to use the identity here where my a here is going to be what? You need to make sure that you see the a is going to be n times arc cosine x, and your b is going to be arc cosine x, right? So that's your a and b, and then I got the a plus b and a minus b for each term. So it's going to turn out to be, what is it, 2 times cosine of n times arc cosine x, and then times, what is it, cosine of arc cosine x, which was our b. Right? So that's what I've got. And as you can see, cosine of our cosine x would be simply x, isn't it? And that's actually the definition of a Tn x. So we have 2x times Tn x as desired, right? So that's the given form, right? No problem, right? So that's correct. So we show the third identity as well. So let's go with the induction for this nice polynomial problem. It says dnx will be always what? A polynomial of degree n. And then, you know, the basic step you already proved for n equal to 1, you showed that it was a linear. So that's not a problem. Let's directly jump into the induction hypothesis. So if we let n equal to k to be true, then we know, I'm going to claim that tk is a degree k polynomial. Okay, so that's going to be written as a ak x to the power of k, where it's the highest power of that polynomial, ak minus 1 x to the power of k minus 1 plus whatever, and then the constant term is what I've got. Okay, and now if I go with the tk plus 1, I want to show that it will be actually degree k plus 1 polynomial, right? But, you know, for that one, of course, you know, it's always about the follow-up process, meaning if there's any term that you already, proved, you always try to use substitution. So what I mean by that is this identity I can use for free because we already proved. You don't need to prove it. You don't need to give proof all the time to use a theorem that you already have proved before. So for that one, if I replace the n with k, then you realize tk plus 1 will be defined as the 2x times kx minus tk minus 1 of x, right? That's what we have. And yes, you know, then I'm encouraged to use the induction hypothesis for proving by induction. You're assuming that the tkx is a degree k polynomial, right? And then on top of that, I'm multiplying the linear factor here. I'm multiplying by the linear factor there. So your polynomial is going to have a leading term as the 2ak x to the power of k plus 1, and then the remaining term, and where it's got all smaller degree, right? They all have smaller degree. It's got all smaller degree than the leading term, where now the leading term is, we got the degree of k plus 1. So now then we can see that tk plus 1 will be then given as a degree k plus 1 polynomial, which proves the result. Okay, so here what is very important is that you try to always use the identity, but that's not the end of it. But for the induction, we always have to use induction hypothesis as well. So for this one, yes, we are using the induction hypothesis of the tk being the degree k polynomial, and the problem is solved. So for that one, Chebyshev polynomial is a very popular kind, and I want you to use that. Okay. Sure, let's have a look at this one. So for this one, part A, it's actually quite nicer. It's nicer than the previous exam questions because we were not given the sum to product formula or any identities that we had to use. But then it has given me to use this formula. So you know you should gladly use it. Okay. So in order to prove it, either you can go from the left to the right or right to the left. But you know obviously right to the left is better. And that's a sakokosa. That's a sine compound, isn't it? With the difference in sign. So it's gonna be sine of 2n plus 1 x minus x. So if you expand, then you are left with just the sine 2nx, and it's good to go. Right? So that's part A. So that's great. Okay, so that's the induction statement. That's the induction statement. And what I want to do for the induction statement is obviously proof for the result to prove. And so, you know, suppose you got the induction hypothesis being true for that one. So I'm going to go with cosine x. So the result to prove is going to be, what is it? The cosine x, and I'm going to add up to, what is it? Cosine 2k minus 1x plus, and I'm going to move into the next term, 2 times k plus 1 minus x, so it's going to be cosine 2k plus 1x is what I've got, okay? So that's my induction hypothesis, and result to prove. So my aim here is to show that it's going to be given as a sine 2k plus 2x over 2 sine x is what I've got, right? So that's what I want to show. And on the left-hand side, what you realize is that for that one, that is going to be replaced by what? On the left-hand side, that's going to be replaced by my induction hypothesis. Oops. That's going to be replaced by my induction hypothesis as a sine 2kx over 2 sine x. So it's going to be replaced as a sine 2kx over 2 sine x is what I've got, right? So that's great. And I'm gonna add by the next term, which was cosine 2k plus 1x. So if you add them together and then put it into the common denominator, right? Obviously, it would be better to put it into the common denominator. So what I'm going to do is to put it as a 2 times sine x over 2 times sine x is what I've got, right? So that's great. And yes, on the numerator, what you realize is got the cosine and sine, right? So for that, that tells me to use the product to sum formula. So for that one, 2 times cosine, sorry, if I scroll down, what I want to do here is to change that into, what is it, the product to sum formula. So let's do that. So here, if I got that x and multiply, so it's got the cosine and sine, so that means it's a difference of a sine compound. Now I hope you naturally see that very quickly. So that's going to be 2 times sine, and I'm going to add them together, so that's going to be, what is it, 2k plus 2x, right? And then times, sorry, not plus, times, but I don't know why I put the 2, haha, sorry. But it's a sine a plus b minus sine a minus b. So if I do that, it's going to be 2kx. So that's what I've got here, right? So if you plug it in and then you see that sine 2kx cancels out, so I got the result to prove, and you can write down the conclusion. That's fine. It's a very similar fashion from what we have done. But for this one, like we have mentioned before, every time you do the induction of a such kind, it's very likely that they're going to follow with a question that you got to use the identity. So let's use it. So it's got adding of 2 terms. So I'm going to let n to be 2. So that's going to be sine, what is it, 4x over 2 sine x is what I've got. So I replaced the left-hand side as such, and then that's same as half. Okay, and my job is to simplify as much as I can. Well, the thing is, now I got the 2 cancels out. That's great. And I'm going to rearrange to the left-hand side and then shift that to the left-hand side again, so that you can convert the equation as the following. It's going to be sine 4x minus sine x is equal to 0. So that's the same kind, right? So that's great. And my domain was given to be from 0 to pi. Okay, so that the denominator will be defined. So that's great, because it cannot be 0 in that interval, right? So that's great. And here, what I want to do here is every time it's the difference of a sign or difference of any trig ratio, you want to use sum to product. And if you remember, now I got the difference of a sign, only the leftover product will be the cosa, right, from the sine compound angle. So from that one, I hope you see that clearly, because that's what we've been practicing all the time, is that the left-hand side here is going to be 2 times cosine, and then it's going to be sum of that angle divided by 2, so 5 over 2x. And sine of the difference of that angle over 2, so 3x over 2 is equal to 0 is what you want to do. Okay? That's great. Then I'm given, what is it, the domain from 0 to pi, and then let's solve it. So for that one, you see, it's going to be 0, 5 over 2x, and 5 over 2 pi. And for that one, for the cosine to be 0, right, 5 over 2x has to be pi over 2, and then 3 pi over 2. So I got 2 solutions in this given domain that makes the cosine to be 0. So if I rearrange, what do you get? The x is going to be pi over 5 or 3 pi over 5. I got 2 solutions. But if I look at the next one here, my friend, what do you see? 3x over 2 is defined from 0 to 3 pi over 2. And for that one, 3x over 2 is going to be simply pi. Right? For the sign to be 0, you got to have an integer multiple of pi. And from 0 to 1.5 pi, only the 1 pi is the possible answer. So therefore, x is going to be 2 pi over 3. So as you can see, for that trig equation, in this given domain, how many solutions do we have? We have 3 solutions. So make sure you always choose the best, right, optimal identity rules. Okay, for this one was the working with the sum to product. So that's great. Let's move on to the next question here. So sure, ask me to prove this. What is it? This is a complementary angle, or we call it the co-function identity. Okay, so either way is fine. But yeah, for this one, you can prove it by compound angle. That will be the simplest approach in this one. You could show by the unit circle, but do not bother because they didn't mention anything not to use compound angle, so it's okay. So I'm going to use sine cosine, and then sine power of 2 is 1, and cosine power of 2 is 0. So for that term, it's going to become 0. So I can end up having cosine x. So that's great. And now, so this induction involves a derivative. So let's try to differentiate. So for that one, if I differentiate only once, right? If I differentiate this only once, by using the chain rule, it's going to be a times cosine ax. So that's great. For which you remember that it's going to be, what is it? Can be replaced as the sine, right? So it's going to be a times sine. And if I let that to be my theta, you have a ax plus pi over 2. So as you can see, that's the result that we wanted to have for n equal to 1, no problem, right? And then let's go for the induction hypothesis implies the result of proof. So suppose you're differentiating k many times. Let's suppose that the induction hypothesis is a to the power of k sine ax plus k pi over 2. Okay, so that's lovely. And here, my aim here is to show fk plus 1 of x is equal to a to the power of k plus 1 sine, what is it, ax plus k plus 1 over 2 pi. So that's my aim here, all right? So that's great. And if that's my aim, right, if that's my aim, what we want to do here is to start with the one side, and maybe I like to start from the left-hand side because it tells me to use it gives me the way to use the induction hypothesis more directly. So that will be the first derivative of what we already have differentiated k many times. Right? So that's the rule of differentiation. And for that one, now I'm very happy because I can now use the induction hypothesis because we already got the kth derivative as the following. Right? So that's great. So I'm going to differentiate this once again. Right? Then if I do, I got the a to the power of k times, what is it? Cosine of ax plus k pi over 2. But then by the chain rule, you got to multiply by the derivative of inside, which was a linear function. So you should only multiply by its coefficient, which is a. So that's going to raise the power by 1 more. So now I have a to the power of k plus 1. So that's great. Okay, very good. And then, yeah, that is equivalent to using the cofunction identity. That is actually equivalent to, what is it? Yeah, you're absolutely right. So that if I let that to be my theta, that's going to be using the cofunction identity sine ax plus k pi over 2, and now I'm going to add by pi over 2, as you can see. So then it becomes k plus 1 over 2 pi, which is the result proof that we wanted to use. So for this one, the reason I brought is that, yes, for the trigonometric induction, it doesn't necessarily have to be using always the sum to product or product to sum formula. Sometimes, as you can see, inverse function composition or derivative is also very popular. Okay, so let's move on to the next question. So here, yes, that's great. It also uses a derivative, but the essence of this practice was to see using the identity. So I'll probably not talk about this. Yeah, I will not talk about this because it's just a derivative, and the essence is to use more on the trig identity. Okay, so I will skip this one so that I conclude this video with the nice 50 questions. I think it's better to have like the complete number rather than 51, right? Okay, so we just went over like essential 50 many questions on the trigonometry and using a lot of identities and equations and functions and sketchings and whatnot. So please revise them. So I hope you realize I handpicked like the unique style of questions so that it does not repeat. That means each of these questions can have a 3 or 4 sort of a similar style type of questions in the exam. So actually you are looking at least the question bank of 200 questions, right? Because we were going over like the unique style of what has appeared in the exam. But over the course of time, they might have just changed the numbers. So what you're really looking at is 200 questions, okay? So that means you shouldn't just practice with what you have seen, but have a look at like the same or similar style questions which appears a lot often on books and exams. So you cannot make excuse of not being able to find such questions because it's everywhere in the exam. But now you change with the terms or signs or numbers. So that's okay. So really, the essence of 50 questions is to efficiently go over the 200 questions. Okay. So with that summary, I finished this lesson, and then hope to see you in another revision video for other topics. That's it for me today. See you next time.